Welcome back to Sleep Nova. Sit back, relax, and don't forget to comment where you're watching from down below. It's amazing seeing people all around the world supporting my small channel. Now, enjoy the show. Night after night, for billions of years, they have watched from the darkness. Moons, those pale, silent companions, have hung in the sky over every epoch of Earth's history. Long before any human drew breath, our moon cast its gentle light and stark shadows across primordial oceans and nascent continents. It lit the way for the first creatures that crawled onto land under its silvery glow. It has been a witness to all of our story. Imagine a night 100 million years ago, when the moon's pale disk shone down on primeval forests and the backs of dinosaurs. Those ancient giants cast shadows by lunar light among the ferns, unaware that the same moon would later glow upon early humans building fires on the savannah. The moon looked down on all of them, unchanged as ages passed. Through extinctions and renewals, through the drift of continents and the rise of consciousness, it kept hanging in the sky. By the time our species arrived, the moon was a familiar beacon overhead. It saw every ritual dance in its honor, every lover's whisper under its radiance, every explorer who dared to reach for it. In the stillness of midnight, the moon looms as a quiet guardian. Its face, scarred by ancient craters, glows with a cold fire, illuminating the night, but never speaking a word. Yet in its silence, it has shaped the rhythms of life. The tides rise and fall to its tug, a planetary heartbeat set to the moon's pulse. In its waxing and waning, humans have seen a mirror of time's cycles, growth and decay, birth and rebirth. Its cool light has guided travelers, stirred the imagination of poets, and provoked the curiosity of scientists. It is our closest celestial neighbor, and for much of human existence, it was the most mysterious object we knew. But the moon in our sky is not alone in the cosmos. It is one of dozens of such natural satellites in our solar system, and countless more in others, each with its own story. They are as varied as the worlds they orbit. Some shine with icy shells, some seethe with volcanic fury, some hide oceans beneath their crusts, and some are mere shards of rock tumbling in irregular paths. They are the silent watchers not just of Earth, but of every planet they accompany, casting light and shadow across the history of the solar system. This documentary journey is an odyssey across time and space, an immersion into the world of moons. We will trace the arc of their narrative, from the ancient myths woven about our moon to the bold exploration of distant moons by spacecraft, from the violent cosmic dances that birthed them to the subtle gravitational embraces that guide their motions. We will stand on the cratered shores of our moon and feel how it shaped Earth's destiny. We will voyage outward to witness fiery Io, icy Europa, and enigmatic Titan. We will delve beneath alien ice looking for the stirrings of life and soar alongside spacecraft as they reveal these new frontiers. Through poetic reflection and scientific insight, we will see moons not as mere rocks circling planets, but as dynamic characters in the grand story of the cosmos. These are worlds that orbit something greater, yet each is a world unto itself. They teach us about creation and chaos, stability and change, and perhaps even about ourselves. Let us begin under the moonlight that has bathed our planet since time immemorial. Let us listen to the silence of the moon and imagine the tales it could tell of Earth's earliest days, of the creatures that evolved under its glow, of the humans who gazed up and found meaning in its face. The story of moons is the story of companionship in the heavens, of smaller worlds bound to larger ones, influencing and illuminating each other in an eternal cosmic dance. And as we explore these stories, we may find that their light guides us not just across the night, but toward understanding our place in the universe. Ancient eyes and mythic tales. Before the age of science, The moon was a canvas for human imagination. In the deep nights of prehistory, our ancestors looked up with wonder and wove stories to explain the glowing disk that waxed and waned overhead. To them, the moon was more than a rock in the sky. It was a deity, a guide, a timekeeper. Each culture filled the lunar silence with its own voice. Imagine a campfire tens of thousands of years ago, flickering beneath a full moon. A storyteller gestures at the bright orb and recounts how it came to be. Perhaps it is a celestial huntress riding a silver chariot across the sky, as the ancient Greeks believed when they personified the moon as Selene, her face aglow in nightly vigil. Or picture the people of ancient China celebrating the autumn full moon with lanterns and mooncakes, telling of Chang'e, the woman who flew to the moon and lives there forever with her jade rabbit companion. In the myths of the Maya, the moon could be a goddess like Ishel, pouring her light down as a blessing on crops and people. Across the world, countless legends cast the moon as a powerful presence, sometimes male, often female, always influential. These myths carry deeper truths about the moon's importance. Early peoples noticed that the moon's cycle of phases matched the rhythms of nature. The word month itself comes from the moon's cycle, and many ancient calendars were built on its changing face. With roughly 29 days between full moons, the lunar cycle offered a natural unit for measuring time. Under the steady beat of those cycles, humans learned to predict the coming of seasons and tides. The moon became a clock in the sky. In coastal communities, the link between the moon and the ocean's tides was observed and ingrained in law. Fishermen timed their outings by the phase of the moon, knowing the waters responded to its pull. Farmers planted and harvested by planting moons and harvest moons, guided by lunar light and timing. The moon also became a beacon for navigators and travelers. Before artificial lights, its glow on a clear night could illuminate paths and reflect off rivers to guide boats. It's no wonder that full moons inspired gatherings and celebrations. The bright nights were a gift from the sky. In various languages and traditions, each full moon had a name reflecting the seasonal law. The wolf moon of deep winter, the flower moon of spring, the hunter's moon of autumn. Each name was a testament to how intimately human life was tied to lunar rhythms. Yet even as people wove tales about our moon, they began noticing that other lights moved across the heavens too. The 5 wanderers we now call planets were known to ancient stargazers, but it wasn't until the invention of the telescope that humanity discovered those planets had moons of their own. That revelation came in the early 17th century and upended our understanding of the cosmos. On a clear January night in 1610, an Italian mathematician named Galileo Galilei pointed his homemade telescope at Jupiter, a shining point in the sky. What he saw astonished him. Near that planet were 4 star-like dots, invisible to the naked eye, that changed position each night. At first, Galileo thought these might be background stars, but as he tracked them, he realized they were orbiting Jupiter. In a letter, he marveled that he had found 4 wandering stars circling a world other than Earth. These were the moons Io, Europa, Ganymede, and Callisto, the first moons ever observed beyond our own. Their existence was a revelation. Here was proof that not everything revolved around Earth. The discovery of Jupiter's moons showed a mini solar system in its own right, with moons dancing around a giant planet, just as Copernicus had dared to suggest that Earth dances around the sun. Galileo's discovery was met with awe and controversy. The idea that moons orbited Jupiter challenged the prevailing belief that Earth was the fixed center of all celestial motion. Yet the evidence was literally before Galileo's eyes. Night after night, he watched those moons shuttle back and forth around Jupiter. It was as if he had invited the heavens to divulge a secret. Other worlds have their own companions. His findings, published in Sidereus Nuncius, electrified Europe. Suddenly, the moon was not unique. It was one of many, and the universe seemed far larger and more complex. The discovery tide did not stop with Galileo. As telescopes improved, astronomers found that Saturn, too, had moons. First Titan, spotted by Christian Huygens in 1655, and then additional moons by Giovanni Domenico Cassini in the following decades. They noticed Saturn's rings as well, mistaking them at first for moons or odd appendages until their true nature became clear. In 1671, Cassini observed Iapetus, a moon of Saturn that intriguingly seemed bright on one side of its orbit and dark on the other, hinting at exotic surfaces that would much later be explained. By the 18th century, the hunt for moons expanded to the new planets discovered. Uranus, found by William Herschel in 1781, came with at least a pair of moons. Neptune, discovered in 1846, revealed its largest moon, Triton, just days later when astronomer William Lassell pointed his telescope at the new blue world. Each of these findings added a piece to a grand timeline of discovery. From a single moon known to ancient humans, we grew aware that moons are abundant. By the 19th century, the count of known moons was climbing. Jupiter's count rose beyond the 4 Galilean moons as fainter ones were caught on photographic plates in the late 1800s. And that count would explode in the late 20th and early 21st centuries. Today we know Jupiter has nearly 80 moons, Saturn over 80, and even Uranus and Neptune have dozens among them. With modern telescopes and probes, scientists keep discovering tiny new moons, often captured asteroids or shards of past collisions that add to the rich menagerie orbiting each planet. Our cosmic neighborhood was teeming with satellites, some as large as planets, others small and irregular. The word moon itself broadened from meaning the moon of Earth to a whole category of objects orbiting planets. Through it all, the myths and wonder persisted. For common people in earlier times, scientific discovery didn't immediately erase the moon's magic. If anything, seeing Jupiter's moons through a telescope might have felt like peering into the divine realms once reserved for gods. The moons of Jupiter were even given mythological names: Io, Europa, Ganymede, Callisto, after lovers and companions of the god Jupiter, a tradition Johannes Kepler had suggested. It was as if, even in science, we acknowledged that these newfound worlds deserved to be woven back into the tapestry of myth. By the dawn of the 20th century, humanity had mapped the motions of many moons, yet they remained points of light in our instruments, their true nature still a mystery. We knew their orbits, and in some cases their sizes. But what were they really like? Were they like our moon, rocky and cratered? Or were they entirely different, perhaps harboring secrets unknown? The ancient questions persisted in new forms. And as the stars of discovery aligned, we prepared in the mid-20th century to actually visit one of these distant orbs and see for ourselves. But before that bold leap, another question loomed. How did these moons come to be in the first place? Origins in cosmic collisions and embraces. To understand the origin of moons, we must travel back to the chaotic infancy of the solar system, back to a time of swirling disks of gas and dust, of nascent planets coalescing and colliding. Moons are born in violence and in grace, in cataclysms and quiet captures. Their origins are as diverse as the moons themselves, each a story of a smaller world coming to belong to a larger one. One path to becoming a moon is to be born alongside your planet, as siblings in the cosmic nursery. In the young solar system, as giant planets like Jupiter and Saturn formed, they were surrounded by whirling disks of gas and rubble, miniature versions of the disk that formed the sun and planets. Within these circumplanetary disks, material clumped together, layer by layer, eventually growing into the moons we know today. Imagine Jupiter as a newborn king surrounded by a swirling court of dust. Over time, that dust gathered into larger pieces, which drew in more material, building up 4 large moons. Io, Europa, Ganymede, and Callisto, the Galilean moons, likely emerged from Jupiter's disk in this way, like pearls forming in the planet's orbit. In this co-creation, the moons inherited an orderly, flat orbit around their planet's equator, circling in the same direction that Jupiter rotates. They are, in essence, the children of Jupiter's youth, born from the same cradle that fashioned the planet itself. But not all moons share this gentle origin. Some are wanderers that strayed too close to a planet and could not escape its gravity. These moons were not born of their planet, but rather adopted. We call them captured moons. Picture a lone asteroid or perhaps a dwarf planet traveling through space, passing near a much larger world. If conditions are just right, the speed, the angle, maybe the intervention of a third body's gravity, the smaller object can be snared, entering into orbit and becoming a moon. Mars's two tiny moons, Phobos and Deimos, are thought to be captured asteroids, cosmic wayfarers grabbed by Mars long ago. They are irregular in shape, dark and battered, very much like the rubble in the asteroid belt from which they likely came. Their capture may have been assisted by a chance encounter or the drag of the early Martian atmosphere. Phobos and Deimos now dutifully circle Mars, but their origin in the sky is written in their odd shapes and carbon, rich composition, so unlike the red planet they orbit. The giant outer planets, Jupiter, Saturn, Uranus, Neptune, have many moons that fit this description: small, lumpy, and often with wild tilted or retrograde orbits, as if caught by surprise. Neptune's largest moon, Triton, stands out as an extraordinary case of capture. Triton orbits Neptune backwards on a tilted path, a clear sign it did not form alongside Neptune. Long ago, Triton may have been a solitary dwarf planet roaming the Kuiper belt until Neptune's gravity ensnared it. The capture of Triton was likely a tumultuous event. Neptune may have had a system of its own small moons that were shattered or ejected in the process. Triton, now bound to Neptune, slowly settled into a circular orbit, but its backward journey remains a scar of its past. It is a migrant from the solar system's fringes, now forever circling an adopted planet, destined in the far future to spiral inward as Neptune's gravity inexorably saps its energy. Then there is perhaps the most dramatic birth of a moon, creation by cosmic impact. Our own moon is the exemplar of this violent genesis. In the young Earth's history, about 4.5 billion years ago, our planet was not alone in its orbit. A Mars-sized protoplanet, often called Theia, was on a collision course with the early Earth. In a titanic impact, Theia struck Earth with unimaginable force, shattering itself and ejecting a vast cloud of molten rock and debris into Earth's orbit. The Earth was left molten and reeling, its day perhaps shortened to a frantic 5 or 6 hours. But from the wreckage, a new entity emerged. The hot debris flung into space gradually coalesced, drawn together by gravity. Within a span of only a few years, perhaps even just a few months, as some simulations suggest, the glowing ring of debris gathered into a sphere. This newborn moon was an incandescent orb of magma hovering above a roiling Earth. Over time, it cooled and solidified, taking on the face we recognize today. This giant impact hypothesis, as violent as it sounds, elegantly explains many of the moon's known traits. The Earth and Moon, for instance, are made of the same basic stuff. Lunar rocks brought back by Apollo astronauts bear the chemical fingerprints of Earth's mantle. It's as if the moon was once part of Earth, which indeed, in this scenario, it was. The collision gouged out material from Earth and mixed it with pieces of the impactor, creating the moon as a blend. The physics of such an impact also explain why our moon is relatively large compared to Earth, and why it orbits in the same plane as Earth's orbit around the Sun, rather than exactly around Earth's equator. It was born of a collision that had nothing to do with Earth's gentle rotation, and everything to do with orbital dynamics and chance. For years, scientists debated alternative theories. Perhaps the moon was captured, or perhaps Earth spun so fast in its youth that a chunk flung off, or that Earth and Moon simply formed side by side. But none of those theories matched the evidence as well as the giant impact. The capture theory struggled to explain the Moon's composition, and such a large capture is improbable. The fission idea couldn't account for where the energy to throw off a moon came from. Co-formation didn't explain the differences in iron core size between Earth and Moon. The giant impact, in contrast, gives a dramatic narrative that lines up with the chemical clues. A moon made mostly of earthly material, but lacking heavy iron, and a system still dynamic today. The Earth's moon may be the child of catastrophe, but it forged a new stability. In the aftermath of that impact, Earth gained not only a satellite, but a guardian of sorts, a big moon that would exert a gravitational influence on Earth for eons to come. That story is unique in our solar system. None of the other rocky planets ended up with such a massive moon. It suggests that chance and circumstance, an ill-fated collision at just the right angle and size, can create a moon where otherwise there might have been none. Yet even the giant impact scenario isn't the final word. Scientists continue to refine models of moon formation, debating details. Was Theia completely destroyed? Did the moon form from the debris of both Earth and Theia, or largely from one of them? New theories propose even faster formation or multiple impacts. But the broad strokes remain. Earth's moon was born from fire and chaos, a genesis writ in planetary rubble. Meanwhile, out in the cold reaches of Saturn, another kind of moon formation drama may have played out in miniature. Saturn's iconic rings, made of countless icy particles, might be the cradle for new moons. It's thought that at least one moon of Saturn, a tiny one named Enceladus, may have formed from ring material clumping and merging outside the main rings. And looking at those rings, some scientists speculate they are the remnants of a former moon that wandered too close and was torn apart by Saturn's tidal forces, a fate called Roche limit disruption. If so, Saturn's rings are both a graveyard and a nursery, the destruction of one moon giving birth to perhaps others, as the debris in the rings slowly accretes. Across the solar system, the story repeats with endless variations. Some moons grew calmly from disks, some were snared from elsewhere, some were born in fire and fury. Co-creation, capture, collision. These are the three classic ways to make a moon. Each moon's current orbit and composition carry clues of its birth. A prograde, aligned orbit hints at a native child of the planet. A tilted or backward orbit points to a captured outsider. A large moon, rich in the planet's own materials, whispers of an ancient impact. Understanding these origins is not just cosmic genealogy, it also sets the stage for everything that comes after. A moon's beginning determines its size, its composition, its proximity to its planet, all factors that influence whether it might have an atmosphere, geological activity, or even the ingredients for life. Our journey through the origins of moons, then, is more than an origin story. It's the prologue to every tale of tides, eclipses, volcanic eruptions, and possible life that moons might eventually host. From the dust of creation to the flames of collision, the birth of moons is a drama that has shaped the very architecture of our solar system. And nowhere is the effect of a moon's existence more profound than right here on Earth, where our moon's presence set the stage for the story of life. The moon's imprint on Earth. Our moon, born of Earth's fury, has in turn been a gentle sculptor of Earth's destiny. Once the moon coalesced and cooled, it settled into orbit around our planet, and a gravitational relationship began that continues to this day. This constant companion, comparatively large and close, exerted forces on the young Earth that would slowly weave the conditions for a stable, life-bearing world. The influence of our moon is profound, shaping the tides, steadying the seasons, perhaps even nudging life's evolution from sea to land. Stand on a beach and watch the ocean, and you are seeing the moon's handiwork. The tides, those regular risings and fallings of the sea, are primarily a consequence of the moon's gravitational pull. As the moon orbits Earth,
Its gravity draws a bulge of water toward it, causing high tide on the side of Earth facing the Moon, and simultaneously on the opposite side due to inertia. Our rotating Earth carries coastlines into these bulges and out again, producing 2 high tides and 2 low tides each day. Since antiquity, coastal peoples have timed their lives by this tidal rhythm. Fishermen knew the best harvest of clams or fish often came with the outgoing tide, and navigators planned departures by the high tide's depth. But beyond human use, tides were a mixing spoon in Earth's primordial soup. In the planet's youth, when the Moon orbited much closer, tides were enormous. Imagine ancient shorelines with waves tens of meters higher, flooding far inland, and then retreating twice a day, every day. These vigorous tides may have created countless tide pools along rocky coasts, trapping water and concentrated chemicals, then stranding them to dry in the sun before flooding again. Some scientists speculate that these wet, dry cycles, driven by lunar tides, could have been crucial in assembling the complex molecules of life. Perhaps the Moon played midwife to life's emergence, providing the gentle pulsation that encouraged simple chemicals to organize into self-replicating patterns. Over billions of years, the Moon has been slowly moving away from Earth, and the days on Earth have been growing longer. In Earth's infancy, a day might have been only 6 or 8 hours long, blurred by the rapid spin left over from the Moon, forming collision. But the Moon's gravity raised tidal bulges, not just in the oceans, but in Earth's solid body as well. As Earth rotated, these bulges lagged slightly behind the line toward the Moon, effectively pulling back on Earth's rotation like a brake. The energy of Earth's spin transferred to the Moon's orbit, pushing the Moon farther away. Through this cosmic friction, our day lengthened from a frenetic spin to the 24-hour cycle we now find so normal. We live, in a sense, on a tempered planet, tempered by the gravitational tug of the Moon. If you could speed up time, you would see Earth's rotation slowing and the Moon spiraling outward in a graceful, ever-widening helix. And as trivial as a few extra hours in a day might sound, the slowing of Earth's spin and the stabilization provided by the Moon had cascading effects on climate and life. One of the most crucial roles the Moon plays is as a stabilizer of Earth's axial tilt. The tilt of Earth's axis is what gives us seasons. Leaning toward the sun brings summer, leaning away brings winter. But that tilt is not fixed in space. Gravitational tugs from the sun and other planets cause Earth to wobble like a spinning top. Without our Moon, these wobbles could have been chaotic and extreme. Mars, for example, lacks a large moon, and its tilt has swung wildly over eons, perhaps ranging from near zero to as much as 60 degrees, contributing to violent climate shifts. Earth, by contrast, has the Moon's steadying gravitational hand. The Moon's mass helps keep Earth's tilt oscillating only mildly over very long timescales, preventing wild swings. This means our seasonal cycle has remained relatively stable for millions of years at a time, providing a consistent backdrop for life to adapt to. If Earth's tilt were to vary dramatically, ice ages might deepen and last longer, or tropics might swing from boiling to freezing, conditions that would challenge the persistence of complex life. The Moon's presence has been like the weight on a gyroscope, damping the wobbles and ensuring that the pendulum of climate doesn't swing too violently. Climate stability is more than a comfort. It may have been a key ingredient for life's long, slow evolution. Under a stable seasonal rhythm, ecosystems have time to establish, and species can adapt at an evolutionary pace, not constantly reset by catastrophic climate lurches. Consider that our current mild wobble leads to cycles like the ice ages. Even those relatively mild oscillations challenged early humans, but life as a whole persisted and diversified through them. Had Earth's obliquity swung from 0 to 60 degrees on a whim, the planet might have seen periods where the poles pointed directly at the sun and then later rolled on its side. The Moon's steadying gravitational anchor likely spared Earth such extremes. Beyond physics and climate, the Moon has subtly guided the rhythms of living creatures. The night's brightness under the Moon has steered behaviors for untold species. Sea turtles, for instance, hatch on beaches by the thousands and instinctively crawl toward the brighter sea horizon, using the moonlit ocean to find their way. Salmon and grunion fish coordinate their spawning with the highest tides around the full and new moons, laying eggs in sand that will be washed out on the next spring tide. Corals in the Great Barrier Reef spawn en masse on certain nights, linked to the moon's phase, releasing millions of eggs and sperm in miraculous synchronicity under a full moon's light. Even some birds use the moon and stars to navigate during migrations. And ancient human cultures, without electric light, lived by the lunar calendar, planning hunts and festivals by the fullness of the moon. Our very sleep cycles and moods have, anecdotally, been tied to the moon's presence. It's possible that life as we know it has a debt to the moon that we are only beginning to understand. In Earth's deep past, perhaps around 400 million years ago, the moon was closer and tides were stronger. Some research suggests that these strong tides could have influenced the great leap of life from water to land. Fish in tidal pools, trapped by receding water, may have needed to flop to adjacent pools or adapt to breathing air for hours until the water returned. Those that managed such feats survived to pass on traits for air, breathing, and limb, like fins. Over generations, these pressures might have encouraged the evolution of amphibious fish, a stepping stone to true land vertebrates. In this way, the moon's tidal pull might have been an unseen hand, coaxing creatures onto dry land and into a new world of evolution. The moon's influence extends to the invisible choreography of Earth's motion as well. The gravitational dance between Earth and Moon has locked the moon's rotation to match its orbit. But Earth too is moving in response to the moon. The two actually orbit a common center of mass, a point inside Earth, but offset from its exact center. This wobble means Earth's path around the sun is slightly perturbed by the moon's presence. And during solar eclipses, when moon and sun align, the moon's shadow races across Earth, a tangible reminder of how perfectly the moon can sometimes position itself thanks to its influence on our orientation. All these effects, tides, day length, axial stability, biological rhythms, underscore a profound truth. Without the moon, Earth would be a very different world. Perhaps life would have found a way regardless. Many scientists debate just how critical the moon's presence was for life's eventual emergence and persistence. Some argue that life could adapt to any sky, while others point out that our large moon might have accelerated evolution or even been necessary to get it started. What is certain is that the moon has been intertwined with life's saga at every turn. From the gentle night light that enabled nocturnal creatures to thrive, to the tidal heartbeat that mixed nutrients in the seas, to the steady seasons that allowed complex ecosystems to develop, the moon has been a constant, subtle, guiding force. Tonight, when you see the moon's bright disk or its thin crescent hanging in the sky, remember that its presence is not just aesthetic. That gleaming orb has been working for eons, pulling on our oceans, slowing our spinning globe, and lighting a path for life to follow. It is easy to imagine an ancient Earth without a moon, a dark night sky, weaker tides, a planet wobbling in uncertainty. Perhaps such an Earth would still harbor life. But would it have been the same rich tapestry we know? Our moon has been a blessing of stability amidst cosmic chaos, an ever-present partner that turned what could have been a more erratic planet into a gently pulsating cradle for life. In the grand tale of Earth, the moon is a character impossible to ignore, an influence from the skies that has quietly guided the unfolding of our own story. Now, having appreciated how our singular moon has shaped us, we turn our eyes outward again. For as unique as Earth's moon is, it is but one of a vast menagerie. Out beyond our planet, orbiting the other giants of the solar system, are moons of ice and rock that reveal an astonishing diversity of nature's creations. Our moon's story is intimately tied to Earth. What wonders and surprises might the moons of other worlds hold? It is time to leave home and voyage into the outer solar system, where moons abound and each holds its own secrets. A tour of the solar system's moons, diversity of worlds.
Leaving Earth behind, we venture across the solar system to visit the remarkable moons that orbit other planets. Each is a world with its own character, as different from one another as deserts are from glaciers, as fire is from ice. In this journey, imagine flying alongside a spacecraft, sweeping first into the realm of the inner solar system, and then outward past the giants, touching down in thought on one moon after another. Our first destination lies near the roiling clouds of Jupiter. As we approach the giant planet, a speck glowing in golden hues comes into view. Io, the innermost of Jupiter's Galilean moons. At first glance, Io's surface is mottled yellow and orange, like a pizza covered in sulfurous cheeses and sauce. This bizarre coloring hints at the extreme volcanism underneath. Io is the most volcanically active body in the solar system. As our mental spacecraft hovers above Io's alien plains, we see volcanoes erupting in great plumes, spraying molten sulfur hundreds of kilometers high. Lakes of lava glow in red patches across the night side. The ground is coated in sulfur compounds, painting Io in brilliant shades of yellow, white, and green. How did this small moon become a hellfire of activity? The answer lies in the relentless pull of gravity and dance of orbits. Io is caught in a gravitational tug of war between Jupiter and the outer Galilean moons. As it orbits, Io is continuously flexed by Jupiter's immense gravity. Imagine the solid ground rising and falling by tens of meters, squeezed like a stress ball. This tidal heating cooks Io's interior and fuels its prodigious volcanoes. Here on Io, we witness a world in constant upheaval, its surface renewed by fire every few years. It is a land of perpetual change, with mountains taller than Everest, that may only last a few million years before collapsing under Io's geological frenzy. In mythology, Io was a maiden pursued by Zeus, transformed into a cow. In reality, Io is a tortured world, eternally writhing under the grip of its giant overlord. Next, we glide outward to Io's neighbor, Europa. Instantly, the scene changes from fire to ice. Europa is slightly smaller than our moon, and it gleams like a pearl, its surface a smooth, bright expanse of water ice. As sunlight glints off its frozen crust, we see a network of dark streaks crisscrossing the moon, like the cracked shell of an egg. These are Europa's famous lineae, fissures in the ice that have been filled and stained by materials from below. Unlike Crater, scarred Callisto, or Mercury, Europa's surface has relatively few craters, indicating it is young and active. But unlike Io, we do not see volcanoes of molten rock. If Europa is active, it is a hidden activity beneath the ice. Scientists have long hypothesized, and now have strong evidence, that beneath Europa's icy shell lies a global ocean of liquid water, kept warm by the same tidal forces that torment Io. This means that as we float above Europa, below us could be an ocean tens of kilometers deep with more liquid water than all of Earth's oceans combined, sealed under a crust of ice perhaps 20 kilometers thick. Occasionally, our spacecraft might catch sight of a geyser, a faint misty plume erupting at the limb of Europa, evidence that water from below sometimes escapes to space through cracks, just as a whale might exhale a breath into the sky. On Europa's surface, we see shattered plates of ice that look as if they've rafted and drifted, and reddish-brown stains where salts or organics may have upwelled. It's a relatively flat world, no towering mountains, but rather a jigsaw puzzle of ice. If we could land and drill down, we'd eventually break through into an alien sea. In our mind's eye, we plunge into the dark waters of Europa, shining a light into the depths. What might we find? Perhaps the seafloor of Europa has hydrothermal vents, like those on Earth's ocean bottom, where mineral-laden hot water gushes out of rock, providing energy and nutrients. On Earth, such vents teem with life: tube worms, clams, strange microbes, entire ecosystems cut off from sunlight. Could Europa's oceans similarly harbor life, nourished by chemical energy and warmth from below? It's a question so enticing that humans are planning missions to one day pierce Europa's secrets. For now, as we leave Europa, we feel the profound hush of this moon, a still, glistening surface above a hidden, restless sea. If Io is the solar system's volcano, laden heart, Europa is its enigmatic, icy soul, holding its secrets deep under frozen plains. Continuing outward, we meet Ganymede, the giant among moons. Ganymede is the largest moon in the solar system, bigger even than the planet Mercury. As we approach, Ganymede looks somewhat like a scaled-up version of our moon or Mercury, with light and dark patches. But Ganymede has a surprise. It possesses a magnetic field of its own, something no other moon has. Our spacecraft instruments detect the auroras shimmering in Ganymede's thin atmosphere, proof of its magnetic bubble within Jupiter's powerful magnetosphere. Ganymede's surface is a mix of very old, dark, cratered regions and somewhat younger, lighter regions laced with grooves and ridges. It's as if Ganymede tried to undergo tectonic activity in its past, the crust stretching and breaking into patterns, then largely froze in place. Like Europa, Ganymede is believed to have an ocean beneath its surface, but likely sandwiched between layers of ice, perhaps a deep, buried sea that is less accessible. Still, the presence of water, a differentiated interior with a metal core, and that enormous size make Ganymede a world of interest. If we could stand on Ganymede, we'd see Jupiter looming huge in the sky, and perhaps thin wisps of oxygen around us. We might walk on water, ice that is, that conceals a distant ocean below our feet. Next comes Callisto, the outermost large moon of Jupiter, a stark contrast to the others. Callisto, shrouded in darkness at the fringes of Jupiter's domain, appears as an ancient cratered relic. Its entire face is pockmarked like a cosmic shotgun target, saturated with impact scars from eons past. It has no discernible mountains or volcanoes or ridges, just endless craters upon craters, with faint rings around the largest impacts, like ripples frozen in ice. If the inner moons of Jupiter are active or were active, Callisto seems to have never been. It is, in a way, a long dead world, a remnant of the early solar system preserved in cold storage. Yet even quiet Callisto might hide a small secret. Data from spacecraft hint it too could have a slumbering ocean deep inside, beneath hundreds of kilometers of ice and rock. If that ocean exists, it has likely been static for billions of years, undisturbed by significant heating or tidal flexing. Callisto stands as a testament that not every moon becomes a geologic wonderland. Some simply exist, surviving from antiquity with the stories of the solar system's violent birth written in their craters. Leaving Jupiter, we sail on to Saturn, where a multitude of moons awaits in a realm of icy enchantment. The first to greet us is Titan, Saturn's largest moon and one of the most compelling places in the solar system. As we approach Titan, we do not see a cratered moon at all. Instead, we see a hazy orange sphere, its surface completely hidden by a thick atmosphere. Titan is the only moon with a dense atmosphere. In fact, at Titan's surface, the atmospheric pressure is about 1.5 times that of Earth's. Standing on Titan would feel a gentle weight of air around you. This atmosphere is rich in nitrogen, like Earth's, but suffused with methane. High in Titan's skies, methane and other hydrocarbons form thick smog that filters the sunlight to a dim, amber glow. If we descend through Titan's clouds, we would witness a landscape both alien and uncannily familiar. There are rivers and lakes here, but filled with liquid methane and ethane instead of water, for Titan's surface temperature is a frigid 179 degrees, far too cold for liquid water. In Titan's dim noon light, We might see ethane rain falling from the clouds onto broad, mirror-like lakes that stretch to the horizon. There are rolling dunes made of hydrocarbon sand, likely formed from organic molecules that have settled out of the sky. There are even seasons on Titan. Over its 30-year orbit around the Sun, its polar lakes shrink and grow, and clouds cluster in different regions. Titan is a world that eerily parallels Earth in some ways. Wind, rain, rivers, lakes, maybe even cryovolcanoes that erupt not molten rock, but water mixed with ammonia from its icy interior. Beneath Titan's frozen crust, scientists suspect another hidden ocean of liquid water and ammonia might reside, kept warm by the moon's internal heat. Titan thus could have two kinds of habitable zones, one in its dark subsurface ocean and another in the liquid hydrocarbons on its surface, albeit any life that might exist in the latter would have to be very different from life as we know it. As we roam Titan's surface in our imagination, methane rain falls on our helmet visor and pools at our feet. We see the glint of Saturn's rings in the sky through a gap in the clouds. Titan feels like a primordial Earth, but one locked in deep freeze where chemistry, not biology, paints the scene. Not far from Titan, another small moon beckons with a dazzling display. Enceladus. Compared to Titan's enormous diameter of 5,150 kilometers, Enceladus is tiny, only about 500 kilometers across. Yet what Enceladus lacks in size, it makes up for in wonder. This bright, ice-covered moon orbits within Saturn's E-ring, and as we draw near, we see why that ring exists. Enceladus is actively spraying its material into space. Along Enceladus's south pole, great fissures in the ice, fondly called tiger stripes, crack the surface. From these cracks, geysers of water vapor and ice crystals continuously erupt, like a curtain of fine, misty jets. Our spacecraft flies through one of these plumes, and instruments taste the vapor. They find water, simple organic molecules, and even microscopic grains of silica, hinting at hydrothermal vents down in a warm ocean beneath the ice. Enceladus, like Europa, hides an ocean under its shell, and through those tiger stripes it vents the ocean to space, giving us free samples of what lies beneath. The sight is breathtaking. Against the blackness of space, dozens of geysers catch the sunlight, forming a shimmering halo over the moon's south pole. The surface around the area is young and smooth, repaved by fresh icefall from these plumes. It was the Cassini spacecraft that discovered this surprise in 2005, changing forever how we see this moon. We now picture Enceladus as a small, cold world that nonetheless has become a cosmic snow globe of activity. Its internal heat likely comes from tidal flexing, which keeps its core warm enough to maintain a liquid ocean. The water from that ocean, maybe 30 kilometers below, forces its way up through cracks and sprays out, instantly freezing and falling back, or floating away to feed Saturn's rings. If we land near a tiger stripe, we'd be on terrain of pure water ice, possibly feeling the ground tremble from subsurface activity. It would be unimaginably cold on the surface, but just below might lie liquid water and perhaps geothermal vents rich in minerals, again raising that tantalizing possibility. Could life exist there, swimming in a hidden sea and periodically being shot out through a space geyser? Now we venture further out, past Uranus with its retinue of frozen, dark moons. We arrive at Neptune, the outermost giant, where a captured moon reigns. Triton. Triton is Neptune's largest moon and unlike any other in the outer solar system. When Voyager 2 flew by in 1989, it revealed Triton as a pinkish, icy sphere with a polar cap of nitrogen ice and a strange cantaloupe-textured terrain. Triton was a revelation. Despite being far from the sun and in the deep freeze, it was not entirely inert. Voyager's cameras caught sight of dark, wind-blown streaks and, incredibly, active geysers near Triton's south pole. But these were not water geysers like Enceladus's. Triton was spewing nitrogen gas. Invisible sunlight, though weak, was enough to heat darker patches on Triton's surface, causing pockets of nitrogen ice to turn to gas and erupt through the surface, carrying dark soot like particles that then fell back, streaking the landscape. We witness one of these geysers ourselves, a faint geyser, backlit by the dim sun, reaching some kilometers high before the material drifts downwind in Triton's thin atmosphere. Triton's surface is young in many areas, with few craters, indicating it has been resurfaced, perhaps by icy volcanism or other processes. We glide over plains that may have been smoothed by slush or eruptions of water, ammonia mixtures long ago. There are odd, lumpy landscapes that look like melting ice cream, possible signs of past cryovolcanoes. Triton, being a captured object, has an eccentric past. Its capture by Neptune would have generated immense tidal heating at first, potentially melting its interior. Over time, Triton settled into a retrograde, circular orbit and cooled, but the geological memory of that event is written in its relatively complex geology. Triton orbits Neptune opposite to the direction Neptune rotates, which is unique for a moon of that size, another clue of its exotic origin. It is also slowly spiraling inward. One distant day, far beyond our lifetimes, Triton may come close enough to be torn apart by Neptune, perhaps forming new rings. But for now, it's a frozen moon with a thin air of nitrogen, a wintry outpost showing that even in the far reaches of the solar system, moons can be dynamic. As our journey through the solar system's moons comes to an end, we take a moment to appreciate the staggering variety we've encountered. We flew from Io's lava fountains to Europa's secret ocean, from Ganymede's giant bulk to Titan's orange skies and methane lakes, from Enceladus's crystal plumes to Triton's geysers and icy plains. We saw moons that could fit in a small sea on Earth, and moons bigger than planets. We saw fire, ice, atmospheres, magnetic fields, and underground seas, all in worlds that orbit other worlds. Each of these moons is a chapter in the solar system's story, a unique expression of how diverse planetary bodies can be. It's humbling to remember that for most of history, these places were just points of light, or in Titan's case, not even visible under its shroud. Only recently have we glimpsed their surfaces and felt their environments through our robotic emissaries. They have transformed our understanding of what a moon can be. No longer can we think of moons as mere dead rocks orbiting planets. Many are complex, geologically alive, and in several cases, potentially harboring the conditions for life. Our tour has shown us boiling sulfur and freezing methane, stark craters, and ethereal atmospheres. And yet, among all these differences, each moon shares a common role, circling a parent planet, locked in a gravitational embrace. They light up their planet's night skies, just as our moon lights ours, each one a smaller part of a greater whole. With this rich tapestry of moons in mind, we are drawn to wonder, where else in those distant, cold, or hot moons might life have found a foothold, as it did on Earth's congenial world under the influence of our moon? The next leg of our journey delves deeper into that question, focusing on those moons that tantalize us with conditions that could be ripe for life. Oceans and the search for life on moons. Among the myriad moons we've visited in our imagination, some stand out as more than just geological wonders. They stir the question of life. Could any of these alien moons harbor living organisms, or at least the ingredients for life's chemistry? The possibility is no longer science fiction. It is a serious focus of modern planetary science. Particularly, the moons that conceal liquid water beneath their surfaces have captured our hopes. On Earth, where there is water, there is life, virtually everywhere. So what of those moon oceans in eternal night? Could life be swimming in Europa's abyss, or lurking in Enceladus's geysers, or even riding the methane raindrops on Titan? The case for Europa as a habitat begins with its deep saltwater ocean,
which could be tens of kilometers thick and global, containing perhaps twice the volume of all Earth's oceans. Liquid water alone is enticing, but life also needs energy and chemistry. Europa seems to offer those as well. Jupiter's constant tidal kneading not only keeps Europa's ocean liquid, it likely drives geological activity at the sea floor. If Europa's rocky mantle interacts with its ocean, perhaps through hydrothermal vents, there could be warmth and nutrients feeding into the water. On Earth, life thrives around hydrothermal vents in the lightless depths, drawing energy from chemical reactions. Europa could host analogous ecosystems, microbes or more complex life feeding on the chemical energy from inside Europa. The European Ocean is sealed off by ice, but that ice might also do something important. It could cycle nutrients. We saw Europa's surface is crisscrossed by cracks and regions where ice seems to have moved around. Some scientists think that surface oxidants could be transported downward through the cracks or subducting ice plates, providing chemical food for life below. In essence, Europa might have the three key ingredients: liquid water, chemical building blocks, and an energy source. No one knows if anything actually lives there. It remains a profound mystery. But if one day we were to drill through Europa's ice and drop a submersible, we might find a whole ecosystem of alien microbes or pale blind fish analogues gliding through the dark. Or we might find nothing at all but a sterile sea. Yet as long as that ocean is there, Europa will beckon as one of the best places beyond Earth to search for life. Then there's Enceladus, the little moon that surprised us with a direct invitation to sample its ocean. Enceladus's plumes jetting into space provide a literal taste of its subsurface sea. When the Cassini spacecraft flew through those geysers, its instruments detected organic molecules, including some fairly complex ones, and tiny grains of rocky particles that could only be formed by hot water interacting with rock. This was a smoking gun for hydrothermal vents on Enceladus's seafloor. Moreover, in 2023, scientists announced that those icy grains contained phosphorus, an element crucial for life, which had been a missing puzzle piece in evaluating Enceladus's habitability. In one swoop, Enceladus offers water, organics, and key minerals, an entire chemistry set for life. The energy clearly exists too. Something drives those plumes, and presumably it's heat from below. Enceladus is small, which suggests its ocean might be in contact with a rocky core that's being flexed and heated. If one could dive into Enceladus's ocean, would it be a dead, dark sea? Or might one find microbial mats around warm vents? Or maybe some exotic life forms that evolved entirely independently of Earth? We cannot help but wonder. Unlike Europa, where a thick crust makes direct exploration challenging, Enceladus conveniently sprays its ocean into space, making it easier for a spacecraft to analyze for signs of biology, perhaps complex organic compounds, or even traces of cells or their remnants in the ejected ice. Titan presents a very different potential for life. On Titan's frigid surface, the lakes and rivers of methane and ethane form a chemistry that is likely too cold and too alien for Earth, like life. Water there is locked up as rock, hard ice. If life exists on Titan's surface, it would have to be something that drinks liquid methane instead of water, a truly novel biochemistry that we can only speculate about. Some astrobiologists have mused about methanogenic life, creatures that use liquid hydrocarbons as a solvent and perhaps breathe hydrogen and exhale methane, but this is highly hypothetical. Titan's surface environment is so cold that reactions happen slowly. It might be tough for life to get started. However, Titan is rich in organic molecules. The atmosphere and surface are a laboratory of prebiotic chemistry, where sunlight break apart methane and nitrogen, forming carbon, rich compounds that rain down. Titan's smog is literally a shower of organic matter. Some liken Titan to a deep freeze version of the early Earth's chemical soup minus the liquid water. While surface life is speculative in the extreme, Titan also, intriguingly, likely has a subsurface water ocean beneath its ice crust. So Titan might have two environments of interest: a cold surface with exotic chemistry, and a hidden water ocean where more familiar life could conceivably exist. If there is life in Titan's ocean, it would be completely cut off from the surface, evolving in the dark with perhaps only the faint trickle of chemical nutrients from rock and ammonia antifreeze to keep it liquid. It's a far cry from the rich brew of Enceladus or Europa, but Titan surprises us at every turn, so who can say? Even Ganymede and Callisto, those Jovian moons we thought rather inert, may harbour deep oceans beneath thick ice layers. Ganymede's ocean is likely sandwiched between ice, which might limit its habitability. Callisto's ocean, if it exists, is also entombed. These places seem less likely abodes for life, but until we explore them, the possibility, however remote, remains. Triton at Neptune, too, could have had a subsurface ocean when it was younger, and maybe pockets remain today, though it's hard to imagine life surviving the drastic upheavals of Triton's capture and cooling. What about moons without oceans? Could life exist in some other form? Perhaps not life as we know it. Moons like Io are too hostile, bathed in radiation and molten rock. Luna is bone, dry and airless at the surface, though we've found traces of water ice in its shadows. It seems lifeless. Most small moons are like asteroids, inert, with no air or water. So it is the water, rich moons that raise our hopes. Our exploration so far has been like detectives gathering clues. Water plumes here, organic molecules there, heat signatures hinting at liquid below. No definitive evidence of life has been found beyond Earth, but these moons offer some of the most promising hunting grounds. In a way, the search for life on moons has reshaped our idea of the habitable zone. We once thought you had to be at just the right distance from the sun for a planet to have liquid water and life. But Europa and Enceladus show that a moon can have liquid water far outside the traditional habitable zone thanks to tidal heating. So perhaps in other solar systems, moons of giant planets might outnumber planets as places to find life. The thought is exhilarating. Life, bearing moons orbiting massive Jupiter, like planets in distant star systems, or under the ice of Saturn's modest satellites. If we find even simple organisms in one of these moons' oceans, it would suggest that life might spring up wherever conditions allow, even in the dark, under kilometers of ice given water and energy. If, on the other hand, we search thoroughly and find nothing living in these seemingly habitable oceans, that would also teach us something profound, that perhaps life is more rare or needs more specific circumstances than we think. For now, these questions propel us to keep exploring. Planned missions like Europa Clipper will sniff out Europa's environment for chemical signs of life's work. Future concepts imagine sending a probe through Enceladus's plume specifically equipped to detect biomolecules or even cells. There is even a dream of one day sending a lander to drill into Europa's ice, or a submarine to swim in its ocean. As we contemplate these moons with potential for life, we feel a subtle shift in perspective. No longer are we the center of the living universe. Life could be scattered on these little ocean worlds in our own celestial backyard. Imagine looking up at Jupiter in the sky and knowing that on one of those pinprick moons orbiting it, something stirs in an alien sea. Such a realization would forever change our relationship to the cosmos. In the grand scale of the solar system, these moons are tiny, but in their tiny niches they may hold some of the biggest answers. Are we alone, or is life a common melody threaded through many worlds? To find out, we must continue to explore these moon worlds with open minds and meticulous science. And as we do, we deepen our appreciation of how special and varied moons can be. Not just passive satellites, but active worlds that could nurture life in the most unexpected of places. Having pondered life and hidden oceans, we turn now to look at moons in another light, as dynamic worlds with geological stories of their own. Alive or not, these moons are far from static. Some are alive geologically, with volcanoes of fire or ice, shifting crusts, and evolving surfaces. Let us now examine how moons, much like planets, can be volcanic, tectonic, and surprising in their ongoing activity. Geological marvels, volcanoes, geysers, and tectonics on moons. In exploring moons, we have discovered that many are not inert balls of rock, but geologically dynamic worlds. Just like planets, moons can have volcanoes that erupt molten rock or icy slush, quakes that shake their crusts, and tectonic forces that reshape their surfaces. These processes remind us that size and status don't limit geological vitality. What matters is energy. If a moon has internal heat, from tidal flexing, radioactive decay, or leftover heat of formation, it can become a stage for remarkable geological activity. Let's examine some of the ways moons act as living worlds of stone and ice. First, consider volcanism. We traditionally think of volcanoes as mountain cones on Earth, spewing lava, or the great basalt floods that created our moon's dark seas billions of years ago. But on Io, as we saw, volcanism is an ongoing symphony of fire. Io's volcanoes, like the towering plume of Loki Patera or the curtains of lava at Prometheus, are driven by tidal heating. This is a fundamentally different heat engine from Earth's radioactive core-driven volcanism, and it makes Io's entire surface a volcanic canvas. Lava flows hundreds of kilometers long repaint Io's face, and enormous calderas dot its surface. Io's volcanism is so intense that it constantly replenishes a thin atmosphere of sulfur dioxide, and even feeds a giant torus of plasma around Jupiter. We have effectively seen a tiny moon outdoing even Earth in volcanic output, all because it is squeezed by gravity like putty. Our own moon once had its fire, a fact written in the vast mare which are solidified lava from ancient eruptions. Though the moon is quiet now, for the first billion years of its life it saw eruptions flood craters and lowlands with basalt. Even small moons can erupt. Take Jupiter's moon Io as the prime example, but also Saturn's tiny moon Enceladus, where cryovolcanism, volcanoes of water, not fire, operates. Cryovolcanism is essentially the cold region equivalent of volcanism. Instead of molten rock, what erupts is liquid water, or water mixed with ammonia or methane that can flow at very low temperatures. Enceladus's geysers are cryovolcanic in nature. There might also be cryovolcanoes on Triton, and possibly on Titan. In fact, Titan's surface shows some features that scientists interpret as potential ice volcanoes. For example, a feature named Doom Mons appears to be a broad rise with a pit, reminiscent of a volcanic caldera, and nearby flows of what could be once melted ice. If Titan has cryovolcanoes, they could be venting water and ammonia from its interior, perhaps occasionally refreshing the surface or atmosphere with new material. Tectonics, the forces that crack and shift a crust, are also present on moons. We have only confirmed active plate tectonics on Earth, but evidence of tectonic-like processes can be found on moons. Europa's cracked ice plains strongly hint at an ice crust that has pulled apart and maybe even subducted in places, as one plate of ice slides under another, similar to Earth's geological plates. Ganymede's network of grooves and ridges suggests that at some point in its past, its icy lithosphere was stretched and pulled, creating faults and troughs, akin to rift zones on a planet. Even small Enceladus shows tectonic fractures. Its surface has regions of tight, rippling faults and folds, especially around the South Pole, indicating the crust has been distorted by cycles of freezing and thawing, or the stresses from its orbit. Miranda, a small moon of Uranus only about 470 kilometers across, is a bizarre example. It sports giant canyons and patchwork terrain that might have formed from tectonic upwellings or even a reassembly after a shattering impact. It's as if Miranda was broken apart and gravity put it back together in a jumbled way, leaving huge cliffs and chevron like surface regions.
Resurfacing is another sign of geological life. A surface that doesn't stay cratered but is renewed. We gauge a surface's age by how cratered it is. The more craters, the older. When we see a moon like Callisto, saturated with craters, we suspect it's been geologically quiet for billions of years. In contrast, Europa's relatively smooth, crater-poor surface means something erased the craters, likely the movement of ice or flooding of fresh material. Io's lack of many impact craters is explained by its volcanoes constantly burying them. Enceladus has certain regions with almost no craters. Clearly, it has been resurfaced by ongoing geyser activity, laying down fresh snow, like ice. Titan's craters are few and far between, likely because active processes like wind erosion, liquid methane rain carving river channels, and perhaps cryovolcanism all conspire to modify the surface. A fascinating example of resurfacing is Iapetus, Saturn's odd two-toned moon. While not exactly resurfaced by internal activity, it has sweeping dark material coating one hemisphere, likely fallout from dust or perhaps cryovolcanic material from outside. The contrast on Iapetus shows how surfaces can change due to even external processes. Then there are moonquakes and other internal rumblings. Apollo astronauts left seismometers on the moon, and they detected that the moon isn't dead silent. There are moonquakes, some from tidal stresses, some from thermal changes, and some from the occasional meteorite impact. The moon's quakes are mild compared to Earth's, but they tell us our moon still settles and adjusts. In recent years, we've even found evidence that the moon shrinks very slowly over time as it cools, forming fresh scarps and cliffs where the crust has cracked and pushed up. Some of these faults look so sharp and young that they may have caused quakes in the moon's recent past. If our large moon can still creak and quake, imagine the much more active churning inside moons like Europa or Enceladus.
Some moons have magnetic personalities. Ganymede's intrinsic magnetic field points to a liquid metallic core churning inside, which is a form of internal activity. Even if that doesn't manifest in surface geology, it's an internal dynamic process, and we have induced magnetism detected at Europa and Callisto, hinting at conductive oceans moving within.
We also see evidence of expansion or contraction on some moons. For instance, Mercury has shrinkage cliffs. Similarly, as mentioned, our moon has them from contraction. Enceladus's ridges and troughs might indicate cycles of freezing and melting. Triton's weird cantaloupe terrain could be from slow, convective overturn in the ice, a sort of relaxation of the surface. Let's not forget the icy ring moons and how they interact. Some tiny moons like Pan and Atlas around Saturn are sculptors of the rings, their gravity opening gaps and shaping edges. This is a gravitational interaction, but results in geological, like patterns in the ring debris. And some moons like Saturn's Janus and Epimetheus even gently collide and exchange orbits occasionally, though they themselves are too small for internal geology. Their dance is a dynamic process on a celestial scale. What we learn from all these observations is that moons can be as geologically diverse as planets. Being a moon only means it orbits a planet. It says nothing about whether it has volcanoes or not. The presence of internal heat is key. Tidal heating has emerged as a major driver. It powers Io's infernos and Enceladus's fountains, and likely Europa's underwater volcanism. Radioactive decay and leftover heat can drive early activity. Sometimes a huge impact can melt a moon's insides briefly. As we visit these moons as geological worlds, one cannot help but anthropomorphize a little. Io is the restless firebrand, Europa, the secretive ocean, Holder cracking its knuckles now and then, Enceladus, the tiny overachiever, spraying its cosmic fountain, Titan,
the atmospheric enigma, slowly raining and eroding, and Triton, the captured rebel, still venting occasional sighs of nitrogen. Even sedate old Callisto, or far out Oberon, and Titania around Uranus each have stories, perhaps long dormant, but written in chasms and craters, waiting for a future mission to decipher.
The more we see, the more we appreciate how active and varied moons can be. Gone is the notion that moons are boring backwaters. Instead, we find on these smaller orbs an incredible laboratory of geology. From the hellish volcanism of Io, hotter in spots than Earth's volcanoes, to the gentle ice volcano cryovolcanism of the outer moons, to evidence of tectonics that on Earth would signal plate movements. Moons have witnessed and enacted many of the same processes that shape planets, and some unique ones too.
By studying these processes on moons, we also learn more about Earth. Io's tidal heating is an extreme case that illuminates how gravitational energy can geologically transform a body. Europa and Enceladus show what happens when internal oceans interact with crusts, something that might have analogies in Earth's past. Even the moon's slow cooling and shrinking gives insight into how terrestrial planets lose heat. With our geological tour of moons concluded, we have seen worlds alive in one way or another. Now, we turn our attention to some of the anomalies and oddities that defy the typical patterns, the misfits of the moon world, those that are irregular, transient, or just plain peculiar. These include moons that are more like asteroids, moons that come and go, or systems where moons share orbits in a celestial dance. The solar system has plenty of the strange along with the sublime, and in our next chapter, we shine a light on those lunar oddballs and mysteries.
Oddballs and mysteries, irregular, ephemeral, and bizarre moons.
Not all moons fit the mold of spherical worlds with stable, eternal orbits. The solar system is also populated with moons that are decidedly odd. Some are misshapen chunks, barely held together, looking more like asteroids than moons. Others follow peculiar paths or engage in orbital dances that seem to defy common patterns. A few are only temporary guests of their planets. These oddballs and enigmas highlight the playful creativity of gravity and the remnants of violent histories.
First, consider shape. To be round, a moon needs enough gravity to pull itself into a sphere. Many moons, especially smaller ones, lack the mass for that, and instead have irregular, potato-like shapes. Mars's moons. Phobos and Deimos are classic examples. Phobos looks like a battered rock, pockmarked with craters, notably one giant crater that gives it a Death Star-like appearance. Deimos is smoother, having accumulated dust in its craters, but it's lumpy too. These moons are almost certainly captured asteroids, as their shape and composition suggest. They remind us that the line between moon and asteroid can blur. Around the giant planets, dozens of tiny moons likewise are irregular. Jupiter and Saturn each have swarms of little moons out beyond their big moons, often on eccentric or tilted, or even backward orbits. These are captured remnants from the early solar system or fragments of shattered moons. They typically have irregular shapes. Saturn's moon Hyperion is a standout. It's about 270 kilometers across and looks like a giant sponge. Hyperion's surface is bizarrely carved into deep pits, and its density is so low that scientists suspect it's a porous rubble pile that never compacted fully. To top its strangeness, Hyperion doesn't rotate steadily. It tumbles chaotically, its axis wobbling unpredictably due to gravitational perturbations from nearby Titan. If you tried to predict when the sun would rise on Hyperion for a given location, you'd have a hard time. Its spin is that irregular. Another irregularly shaped curiosity is Pan, a tiny moon of Saturn only 35 kilometers across. Pan orbits within Saturn's rings, in the Encke Gap, and has accumulated a skirt of ring particles around its equator, making it look like a flying saucer or a walnut. It has a bulging ridge, essentially a ring of its own, stuck to its equator. Atlas, another little ring moon, has a similar UFO-like look. These ridges likely formed as the moon scooped up dust and ice from Saturn's rings while orbiting within or near them. These mini-moons underscore how moons can shape and be shaped by their environment in surprising ways. Now, binary systems. While no planet besides Pluto truly has a binary moon system where two moons orbit each other around a planet, Pluto and Charon deserve mention. Charon, roughly half Pluto's size, isn't just a moon. Together, Pluto and Charon act like a double dwarf planet system. They orbit a point in space between them, gracefully pirouetting around each other every 6.4 days, forever showing the same face to each other. This mutual tidal locking and the balance of sizes make Pluto-Charon a unique case in our solar system. It stretches the definition of moon, as one could argue Charon is not just orbiting Pluto, they orbit each other. If Earth's moon were a bit larger, Earth and the moon might similarly orbit a point in between. The Pluto-Charon example invites us to consider that in other solar systems, there might be exoplanets with moons so large that the distinction between planet and moon blurs, and they form true binary pairs. Within our solar system's moons, we also see co-orbital dances. Saturn's moons, Janus and Epimetheus, for example, share nearly the same orbit. They are only about 50 kilometers different in their orbital radius, and they race around Saturn in close pursuit. Every 4 years or so, the inner one catches up to the outer one, and they perform a gravitational do-si-do. They exchange energy and effectively swap orbits. The one that was inner moves to the slightly outer orbit, and the outer moves to the inner path. Then the cycle continues. It's a graceful swap that conserves momentum and prevents collision. For a long time, astronomers were confused by observations of what seemed like one moon in that orbit that occasionally jumped position, until they realized it was two. Another strange orbital choreography involves what we call Trojan moons. Two of Saturn's moons, Tethys and Dione, each have smaller moons that reside at the stable Lagrange points, leading or following the bigger moon by 60 degrees in the same orbit. Essentially, the little moons are locked in a gravitational sweet spot, shepherding the orbit of their larger partner. They're like captured attendants, forever preceding or trailing the larger moon. No other example of Trojan moons is known beyond Saturn, but the concept is intriguing. Moons of moons in stable configurations. Temporary moons are a particularly interesting category. Earth, besides our big moon, occasionally has other small mini-moons. These are tiny asteroids captured for a short time. For instance, in 2006, a small asteroid about a few meters in size was captured by Earth's gravity and orbited Earth for several months before drifting away. More recently, another mini-asteroid called 2020 CD3 was discovered orbiting Earth from 2018 until 2020. These temporary moons come and go, usually staying for a few orbits before the dynamics allow them to escape. They remind us that the definition of a moon can be fleeting. A moon can be there 1 year and gone the next. At any given time, Earth might have one or more tiny natural satellites temporarily, and we wouldn't know unless we look carefully with telescopes. Jupiter and other planets likely capture small asteroids on occasion too. Their hills of gravity are larger, but also their real estate is far from Earth, so we notice fewer of those captures. Retrograde moons and inclined oddballs add to the menagerie of strange. Many of the tiny outer moons of Jupiter, Saturn and Neptune orbit backward relative to the planet's rotation. Triton, again, is the largest retrograde moon, captured and forced to dance to Neptune's tune in reverse. These retrograde moons often have stretched, inclined orbits too, suggesting they were snared objects. There are also moons with remarkably eccentric orbits. One of Jupiter's distant moons, S2003J2, loops far out in an oval path, taking years to complete one orbit. Some small Saturnian moons oscillate in strange resonances, like Neptune's inner moons, Naiad and Thalassa. Naiad is in a slightly inclined oval path that bobs up and down in such a way that it avoids ever colliding with Thalassa.
in what's been described as a dance of avoidance. Naiad laps the Lhasa every few orbits, passing above or below it in a choreographed pattern dictated by resonance.
Physical anomalies also intrigue us. Iapetus, Saturn's two-toned moon, aside from its dark light yin-yang coloration, boasts an equatorial ridge of mountains that wraps most of the way around like the seam of a walnut. How did such a ridge form? One theory is that Iapetus might have had a decaying ring of its own that collapsed onto its equator, building a chain of mountains. Or it could be the remnant of Iapetus's youthful spin, when it rotated so fast that the equator bulged and then froze in place as the moon cooled. It remains an odd and picturesque feature, unmatched elsewhere.
And what about moons with rings? It sounds fanciful, but Saturn's second largest moon, Rhea, gave a hint of a possible ring system in some spacecraft data. If confirmed, that would be a moon with its own ring. As of now, it's an open question, and subsequent observations haven't clearly found rings around Rhea, so that mystery endures.
These irregular, ephemeral, and surprising moons teach us that being a moon is not one size fits all. They are the exceptions that prove the rule, and sometimes they break the rules in delightful ways. They speak to the dynamic and often violent processes that populate planets with moons. Captures of passing objects, collisions that shatter a moon into pieces that become new moons or rings, gravitational tricks that allow multiple bodies to share orbits. They also show us how creative nature can be with orbits. As long as the laws of gravity are obeyed, seemingly odd arrangements can persist for millions of years. If you had an artist's eye, you might see Janus and Epimetheus as two dancers swapping positions on a giant stage, or the Trojan moon Telesto as forever surfing the gravitational wave ahead of Tethys. You might see Hyperion tumbling through space like a tossed sponge from the gods, never the same rotation twice, or Phobos slowly spiraling inward toward Mars, destined to either crash into the Martian surface or be torn into a ring in some millions of years. A moon in death throes, gradually succumbing to tidal forces. Yes, even the lifespans of moons can be finite. As mentioned, Triton will likely spiral into Neptune someday far off. Phobos is drawing closer to Mars by a few centimeters each year. Within 50 million years or so, it may break apart under Mars's tidal pull and possibly create a short-lived ring around Mars before raining down. Jupiter's intense gravity may eventually destabilize some of its captured shards as well. The temporary moonlets come and go on human timescales, hinting that the tapestry of moons is still being woven even now. Through these strange moons, we see the solar system not as a static set of clockwork orbs, but as an evolving, changing family with members that sometimes wander in, sometimes wander out, sometimes behave bizarrely. It's a cosmos of surprises. And as we prepare to send more explorers out there, who knows what other odd moons we might find? Perhaps a moon with active geysers of neon, colored chemicals, or a moon that is two halves barely held together, or moons in exotic resonant patterns yet unseen. We now have journeyed through nearly every aspect of moons, their mythic allure, their formation, their effects, their astonishing diversity and geology, and their curiosities. Our attention turns next to how we humans have stepped into this story with our machines and our own feet, through missions that have explored these moons, and how those missions have enriched our understanding and prepared us for even grander adventures to come. Reaching the moons, from Apollo to tomorrow's missions. Humanity's fascination with moons has not remained in the realm of observation and theory. We have boldly taken voyages to these distant worlds, sending spacecraft to uncover their secrets. Each mission, whether crude or robotic, has been a chapter in our unfolding understanding of moons, transforming points of light into real places with landscapes and histories. Let's journey through some of the landmark missions that have explored moons and look ahead to the missions on the horizon. The first tentative steps were robotic. In the late 1950s and 1960s, during the dawn of the space age, Both superpowers, the United States and the Soviet Union, set their sights on Earth's moon. The Soviet lunar program achieved a series of historic firsts: the first human-made object to hit the moon, the first photos of the moon's far side, and later the first soft landing and the first robotic rover. These early missions proved the moon was reachable and prepared the way for something even bolder: landing humans there. In July 1969, the world watched in collective awe as Apollo 11 carried Neil Armstrong and Buzz Aldrin to the Sea of Tranquility. When Armstrong stepped off the lunar module's ladder, uttering, "That's one small step for a man, one giant leap for mankind," a dream as old as humanity was realized. The astronauts found a world of grey dust and rocks under a black sky, Earth hanging blue and bright above the horizon. Aldrin described the lunar landscape as magnificent desolation. Over the course of 6 Apollo missions, 12 humans walked on the moon, exploring different regions, driving a lunar rover across the soil, setting up experiments, and collecting rocks. These samples, returned to Earth, revolutionized lunar science. They told us the moon's composition, its volcanic past, and supported the giant impact theory by revealing the moon's similarity to Earth's mantle. Apollo 8, months before the landing, had already given us the iconic Earthrise photo, Earth rising over the moon's limb, an image that redefined how we see ourselves, a delicate blue marble in the vastness as witnessed from the moon. Apollo ended in 1972, and no human has been beyond low Earth orbit since, marking a pause in human moon exploration. But the legacy of Apollo lives on. In every reflective visor selfie an astronaut took on the moon, our planet is seen small behind them, a humbling perspective gifted to us by those missions. Even as Apollo ended, robotic explorers were gearing up to tour the outer solar system and its moons. In 1979, NASA's twin Voyager spacecraft flew past Jupiter and then Saturn. Voyager 1's cameras, as it swung by Jupiter, captured something astonishing: active volcanoes on Io, the first proof of active volcanism beyond Earth. It was a discovery that made scientists gasp. Until that moment, we assumed moons would be cold and dead. Voyager also sent back tantalizing images of Europa's cracked ice shell and hints of complex surfaces on Ganymede and Callisto. At Saturn, Voyager 1 and 2 revealed Titan's thick, smoggy atmosphere and the spongy Hyperion, and many of Saturn's smaller moons in detail for the first time. These brief flybys were like flipping through a cosmic photo album, each image raising new questions. They paved the way for longer visits. In the 1990s, NASA's Galileo spacecraft became the first to orbit Jupiter. Galileo spent 8 years in the Jovian system, repeatedly flying by the Galilean moons. It confirmed that Europa likely harbors an ocean beneath its ice, photographed Europa's ridges and chaotic terrains up close, and even saw what looked like rafts of ice that had broken and shifted. Galileo also found evidence that Ganymede has its own magnetic field, and hinted that Callisto might have a subsurface ocean too. Meanwhile, Galileo watched Io's volcanoes in action, seeing plumes and red glowing lava, and mapped the resulting changes. This extended exploration turned those moons from curiosities into richly studied worlds. Galileo, however, suffered a stuck antenna, which limited the data return, yet still transformed our understanding of Jupiter's moons. Around the same time, attention turned back to Saturn. The Cassini-Huygens mission, a collaboration between NASA, ESA, and others, launched in 1997 and arrived at Saturn in 2004. For 13 years, Cassini orbited Saturn, a marvel of longevity and discovery. It carried a passenger, the Huygens probe, which in 2005 descended through Titan's atmosphere and landed on Titan's surface, the first landing on a moon beyond our own. Huygens sent back images from beneath Titan's orange sky, rounded icy rocks, a damp riverbed, and a horizon shrouded in fog. It was like standing on a primordial Earth, bitterly cold and alien, yet eerily familiar in geomorphology. Cassini, orbiting above, mapped Titan's surface with radar, revealing lakes and dunes, and it watched Titan's seasons change over the years. Cassini's tour of Saturn's moons was like a grand saga. It discovered the water plumes of Enceladus, flying through them to taste their composition. It imaged Enceladus's tiger stripes in detail and confirmed an ocean beneath its ice. It photographed Iapetus's two-tone divide and dramatic ridge, investigated Hyperion's chaotic tumble, saw jets off tiny moon Daphnis sculpting Saturn's rings, and even witnessed a meteorite crash into Saturn's rings, a tiny collision caught serendipitously. Cassini made hundreds of flybys of Saturn's moons, essentially writing the textbook on the Saturnian system. When Cassini's fuel grew low, NASA chose to end the mission by plunging Cassini into Saturn in 2017. In its final orbits, Cassini gave us unprecedented close-ups of the rings and measurements of Saturn's gravity, a fiery grand finale for an epic mission. As it disintegrated in Saturn's atmosphere, scientists and the public alike bid farewell to a venerable explorer that had, quite literally, broadened our horizons. After Cassini and Galileo, our explorations continued. New horizons flew by Pluto and Charon in 2015, revealing the surface of Charon, the moon half of that binary, in detail for the first time. Pluto's heart and mountains stole the show, but Charon's discovery of a giant chasm and a dark reddish cap of tholins at its pole added to the list of surprising moon geology. Even Neptune's moon Triton got another look, albeit distantly, with Voyager 2. We haven't returned since, but proposals exist to send an orbiter there in the future. Meanwhile, back to Earth's neighborhood, our moon saw renewed robotic visitors. Orbiters like NASA's Lunar Reconnaissance Orbiter, mapping it in high definition, and China's Chang'e program achieving soft landings, including on the far side. These missions found water ice in permanently shadowed craters at the lunar poles, a valuable resource for future explorers. They also continue scientific investigations of lunar geology and even biology experiments. Now we stand on the brink of a new wave of exploration, the era of returning to the moon and pushing farther to the outer moons with advanced probes. NASA's Artemis program is the flagship of human spaceflight in this realm. Named after Apollo's twin sister, Artemis aims to land the next man and the first woman on the moon, focusing on the lunar South Pole region where water ice resides in shadowed craters. Artemis I, an uncrewed test flight of the mighty Space Launch System rocket and Orion spacecraft, flew around the moon in 2022, heralding the return of NASA's crew, capable deep space vehicles. Artemis II will carry astronauts on a lunar flyby, and Artemis III, slated for the mid-2020s, hopes to put boots on lunar soil again. The plan is not just flags and footprints this time, but to establish a sustainable presence, perhaps a lunar base or the lunar gateway, to facilitate ongoing exploration. Living and working on the moon will serve as a testbed for eventual human missions to Mars. One can imagine future astronauts at the moon's south pole, sunlight skimming the horizon as they harvest ice for water and fuel, and look up to see the distant blue Earth and perhaps beyond it, glints of Jupiter or Saturn, moons gazing upon other moons. On the robotic front, one of the most anticipated missions is NASA's Europa Clipper, set to launch in the mid-2020s. This large spacecraft will orbit Jupiter and make dozens of close flybys of Europa, scanning its ice shell with radar, measuring its magnetic field to confirm the ocean's characteristics, imaging the surface at high resolution, and sniffing for any signs of plumes or organic molecules. Europa Clipper's goal is to assess Europa's habitability, essential groundwork, if we ever decide to drill through that ice or send a submarine into its ocean. Around the same time, the European Space Agency's JUICE mission, launched in 2023, is on its way.
By 2030, JUICE will arrive at Jupiter and focus on Ganymede, while also studying Europa and Callisto in flybys. JUICE will give us an unprecedented look at Ganymede's magnetic field, its suspected ocean and surface. Looking further ahead, concepts are being studied for an Enceladus mission that would orbit or land on this tiny moon to directly search for signs of life, perhaps by sampling fresh plume material for complex organic compounds or even cell-like structures. Another mission, Dragonfly, is in development to go to Titan. This one a rotorcraft lander that will launch in 2027 and arrive in the mid-to-2030s. Dragonfly will hop between different sites on Titan's surface, investigating the chemistry of its dunes and possibly the edges of its methane seas in search of prebiotic chemistry or even biosignatures, and to understand Titan's chemistry. Meanwhile, the Japanese Space Agency is preparing the Martian moon's exploration mission to Phobos. Scheduled to launch in the mid-2020s, MMX will land on Mars's moon Phobos, collect samples, and return them to Earth, aiming to reveal that moon's origins. Every mission to a moon brings new wonders. Cassini's findings of Enceladus's habitable ocean were not even on the radar when Cassini launched. We were taken completely by surprise. What surprises might Europa Clipper or Dragonfly or Artemis astronauts have in store? Perhaps plumes on Europa will reveal organic molecules more complex than any found off Earth so far. Perhaps Dragonfly will find that Titan's organic soup has formed something like primitive cell membranes or interesting electrical patterns in the hydrocarbon lakes. Maybe Artemis explorers will discover a new mineral in the lunar craters, or even microbial life hitchhiking from Earth that survived in lunar ice, giving cautionary data for planetary protection. These missions are not just about satisfying curiosity, they carry profound implications. If a future probe finds even microbial life on another moon, it would prove that life is not unique to Earth. If we find an absence of life in places that seem habitable, that too tells us something, that life might be rarer than we assume or needs more specific circumstances. Human missions like Artemis aim to make the moon a part of humanity's sphere, no longer an unattainable orb, but a place where people can work, research, and perhaps one day even mine resources or build observatories. There's also an emotional and cultural resonance to these explorations. Apollo's pale suits against grey dust became an icon of the 20th century. The image of Huygens landing on Titan, navigating by parachute down through orange clouds, fired imaginations about exploring alien skies. Each mission extends our senses. With cameras, we have stood on the slopes of mysterious mountains on the moon and looked back at Earth. We have floated above Jupiter's swirling storms, with Io glowing in the foreground. We have watched a sunset on Titan through a hazy atmosphere. We voyage through our probes, living vicariously through their lens. As we continue to reach out, it's worth remembering that these endeavors are also acts of stewardship of knowledge. We learn not just about those moons, but about Earth by comparison, about how planets and moons interact. And these missions inspire generations. Some who watched Apollo or Voyager are today the ones designing Artemis and Europa Clipper. Our expedition through the history and future of moon exploration underscores a theme. Once unreachable, moons are now within our grasp. We have touched our moon, orbited others, and landed on a few. We have plans to return and even reside for a while. Robotic envoys will soon sniff the air of distant moons and crawl on their surfaces. It's an exhilarating time, blending the spirit of adventure with meticulous science. Equipped with all this knowledge and experience, our perspective shifts when we look up at the night sky now. We don't just see a bright moon, we see a place humans have stood and will stand again. We spot Jupiter as a point of light and imagine the pinpricks of Io's volcanoes or Europa's potential plumes. Saturn's golden dot brings to mind the lakes of Titan and the geysers of Enceladus. These celestial lights have become places in our minds. With our machines and dreams, we have brought the solar system's moons into our realm of experience, if not physical, then intellectual. And with each mission, we become a species not confined to one world, but a bit more at home in the vast archipelago of worlds that orbits our sun.
Now, beyond our sun, countless other stars shine in the night. Around many of those stars orbit planets, and around some of those planets, perhaps moons. Before concluding our journey, let us cast our gaze even farther, to the possibility of moons circling distant exoplanets, and consider what their existence might mean.
Moons beyond our solar system, the quest for exomoons. So far, our tale has stayed within the bounds of our sun's family. But even as we explored the moons of our solar system, astronomers have been pondering a tantalizing question. Do moons exist around planets of other stars? We call such hypothetical worlds exomoons, and finding them is an ongoing quest at the cutting edge of astronomy. If planets are common in the galaxy, it stands to reason that many of those planets, especially the giant ones, should have moons. Perhaps some alien sky has a view as lovely as Jupiter and its retinue. Or perhaps an Earth, like exomoon, orbits a huge planet in a distant star's habitable zone, providing a home for life. Detecting exomoons is, however, even more challenging than detecting exoplanets. Planets themselves often are found indirectly, for example, when they transit their star and cause a tiny dimming of starlight, or when their gravity makes a star wobble. A moon is smaller still, and its effects subtler. Nonetheless, scientists have devised clever ways to hunt for them. One method is to look for slight irregularities in a planet's transit timing or duration. An unseen moon tugging on the planet could cause it to wobble and transit a bit early or late, or produce extra dips in starlight. Another approach is direct imaging. A few large exoplanets have been photographed around stars. A sufficiently large and well-separated moon might one day be directly observed in such images.
In 2018, researchers announced the first compelling exomoon candidate. Using data from the Kepler Space Telescope, they studied a Jupiter-sized exoplanet called Kepler 1625b, around 8,000 light-years away. They noticed hints that this planet's transit was followed by a smaller dip, possibly a Neptune-sized moon trailing the planet. Follow-up observations with the Hubble telescope added evidence that something was there, although the result remains unconfirmed and debated. If real, this exomoon would be far larger relative to its planet than any in our solar system, a reminder that exoplanets continue to surprise us with their diversity. In 2022, another possible exomoon was reported, also quite large, though it too awaits confirmation. Why the focus on giant moons? Simply because our current techniques are sensitive enough only to detect very large moons, likely gaseous or icy, around big planets. We don't yet have the capability to find an exomoon akin to our moon around a distant Earth-like planet. But as technology improves, through new space telescopes and more sensitive instruments, astronomers hope to eventually detect smaller exomoons, perhaps even down to the size of Mars or Earth. The implications of exomoons are exciting. Some scientists argue that an Earth-sized moon orbiting a gas giant in the habitable zone of a star could be a habitable world itself, essentially a moon planet with conditions for life. This scenario, reminiscent of science fiction locales like the forest moon of Endor in Star Wars, is scientifically plausible. A large moon could have an atmosphere, liquid water, and stable environments, all while orbiting a protective big planet. The presence of a giant planet could even shield the moon from excessive asteroid impacts or provide a magnetic field umbrella. On the other hand, it might also bathe the moon in radiation, posing challenges for life on the surface, but perhaps life could thrive underground or underwater. Exomoons also broaden our perspective on where life might arise. We now know to look not just at planets, but their moons. In our solar system,
we see potentially life-friendly environments on moons like Europa and Enceladus. If similar moons exist elsewhere, the galaxy's habitable real estate could be significantly expanded. A star's habitable zone might contain giant planets that themselves are inhospitable gas balls, but their moons could be the true gems. The search for exomoons is a testament to our desire to not only find analogues of our planet, but also analogues of our moon and the rich relationships that moons have with their primaries. It forces us to refine techniques and maybe even build future observatories dedicated to this faint whisper of a signal. Perhaps in the coming decades, we will get our first confirmed detection of an exomoon. And if we are truly fortunate, one day we might even glean information about its atmosphere or composition. Enough to say, for instance, this moon has oceans and clouds.
The existence of exomoons, confirmed or not, also has a philosophical tinge. It underscores that our solar system is not unique in its complexity. The dance of planets and moons is likely a common cosmic theme. Somewhere out there are moons that cause eclipses as seen from their planets' surfaces, moons that tug tides on alien oceans, moons that might glow with bioluminescent life under foreign skies. We have begun to suspect their presence. The next generation of telescopes will no doubt reveal them one by one.
When we finally do find them, exomoons will become part of our ever-expanding narrative of the cosmos. Each new moon discovered around a distant sun will be a reminder that nature's creativity is boundless. The moonlit nights we know on Earth, so special to us, might be a universal experience shared under many skies. And knowing that adds a profound connection. The same way every human culture under our moon found meaning in its glow, perhaps across the galaxy, other beings dance under the light of their moons. For now, exomoons remain a frontier, a promising echo of the familiar in the vast unknown. As our documentary journey transitions from exploring the known moons to reflecting on their meaning, the possibility of exomoons serves as a bridge. It links the concrete knowledge we have gained about moons in our solar system with the tantalizing potential of worlds yet to be discovered, out beyond our reach, but not beyond our imagination.
Reflections. Under alien moons, meaning and metaphor.
Throughout history, the moon has been a mirror, not just of sunlight, but of human thought and emotion. We have cast our dreams, fears, and philosophies onto that gentle disk in the night. Now, having journeyed among the moons of the solar system, we return with a richer tapestry of meaning. We see that every moon, in its own way, is a symbol, and their stories resonate with our own. From our earliest days, the moon was a companion in the dark, a source of wonder and reassurance. It waxed and waned, teaching us about cycles, the idea that endings are not final, for the crescent grows again after the new moon's darkness. In this, people found hope and rhythm. The moon became associated with the cyclical nature of life, time measured in moons, the tide, like flow of fortunes, the rhythms of fertility and growth. Poets compared the waxing moon to a growing child or the blossoming of love, and the waning moon to aging or heartbreak, yet promised renewal in the next cycle. Nearly every culture saw something personal in the moon's face. Some saw a compassionate figure, a goddess who lights the night and watches over lovers and lost travelers. Others saw a clever god, or a mischievous rabbit, or a reminder of heroic stories. These myths, diverse as they are, share a sense of the moon as an object of connection between the heavens and human hearts. The moon was distant, yet felt intimately close, influencing daily life through calendars and tides, and nightly life through its calming glow. It symbolized the known in the unknown, a gentle light amidst darkness. Now consider our new knowledge. Moons are everywhere, not just orbiting Earth. Each planet has its own moonlight in its sky, its own tidal rhythms imposed by orbiting companions. The idea that moons are silent watchers extends beyond Earth. One can imagine a hypothetical being on Jupiter's cloud tops marveling at the dance of Io and Europa, or a being on Titan witnessing Saturn's rings casting shadows in Titan's sky, with tiny Enceladus sparkling as a star, like point. The presence of moons is a universal feature of planetary systems, which suggests something profound. The concept of a smaller body, forever bound to a larger one, is a motif written into the cosmos. It invites metaphor. Are we not all, in some sense, moons? We live our lives influenced by greater forces, the gravity of our communities, our nations, our planet, the sun's energy, the pull of tradition and history. Yet within those orbits, we have our own trajectories, our own landscapes and individuality. To be a moon is to be a follower, a companion. But our exploration has shown that a companion world is still a world. Being gravitationally bound to a planet doesn't diminish a moon's uniqueness. In fact, that relationship can enrich it. Tidal heating can endow it with fire and ocean. Tidal locking gives it a permanent sky view of its primary and perhaps a special stability. In the same way, perhaps being bound to greater things, family, society, the earth itself, does not diminish individuality, but provides context that allows life and meaning to flourish. Moons, by their very existence, teach a lesson of belonging. No moon floats alone in space. Each is part of a system, just as we are all part of something larger, be it family, culture, or the biosphere. And yet, moons also teach resilience and identity. Think of Triton, captured against its will, retrograde and rebellious, yet it settled and became one of the most intriguing moons we know, forging geysers under Neptune's distant sunlight. Or Europa and Enceladus, tiny in comparison to their planets, yet possibly cradling more life potential in their hidden seas than the huge worlds they orbit. Size and rank do not correlate with significance. A small moon can have a global ocean. A giant planet might be a sterile gas ball. Likewise, a single human or small community can harbor creativity, love, and innovation that influence the larger world profoundly. The relationship is symbiotic. The big influences the small, and the small can influence the big. The moon has also always symbolized reflection. It shines, but with borrowed light. In that, there is a deep metaphor. We too shine often with light passed to us by others, knowledge, wisdom, kindness that we have received, and then reflect onwards. Our ideas are illuminated by the great thinkers before us. Our compassion is lit by the love we've been shown. And like the moon, which can cast enough light to show the way in darkness, we too can reflect the light of greater truths or greater goodness into the dark corners of each other's lives. We might also think of the moon as representing the idea of being secondary, yet essential. Planets dominate their moons in gravity, but if you remove the moon, the system changes drastically. Earth without its moon might not have fostered such stable, life-friendly conditions. Jupiter, without its Galilean moons, would lack the most interesting aspects of its identity. In the same way, what orbits around a person or a society, its art, its ideas, its satellites of influence, though secondary in mass or power, might be what truly defines it. A planet without moons is a bit like a leader without companions or a mind without dreams, functional but missing depth and nuance.
Consider also the perspective of standing on a moon looking up at its planet. On the moon, astronauts gazed up and saw Earth, a swirling orb of blues and whites, a sight that moved them to profound introspection. On Io or Europa, one would see Jupiter's banded enormity filling the sky, a constant reminder of a bigger presence. Perhaps this is akin to moments in human life when we stand in awe of something larger than ourselves, standing before the vast ocean or a towering mountain, or contemplating the galaxy on a starry night. We feel small, yet connected to something grand. Moons literally live with that view every day. They know, if one can poetically assign knowledge to them, what it means to always circle something inspiring, and bigger. But they also show that one can have one's own identity in that situation. The people of ancient times could look at the moon and feel both the greatness of the heavens and the personal comfort of that lantern in the sky. There's a balance there of humility and significance. Culturally, the moon often symbolizes the subconscious or the hidden, as the sun symbolizes the obvious and conscious. The moon comes out when the sun leaves, revealing stars, hinting at mysteries. Likewise, exploring the moons of the solar system has been an exercise in illuminating the previously unseen, delving into the mysteries of how diverse nature can be and holding a mirror to our assumptions. Who would have expected that desolate-looking Europa would hide a deep ocean, or that tiny Enceladus would shoot geysers into space, visible to Cassini's cameras? These discoveries were like subconscious truths emerging, showing that reality is richer than daylight logic might predict. We as a species are enriched by these revelations. They remind us to keep an open mind and appreciate the unseen forces and potentials in our own lives and world. The phrase orbiting something greater resonates beyond astronomy. Philosophically, it speaks to a relationship between part and whole, self and other, finite and infinite. We on Earth orbit the sun, a star that gives us life. The sun orbits the center of the galaxy. Perhaps even galaxies orbit some center in a cosmic dance. At every scale, orbiting something greater is the rule. It does not diminish the smaller. Instead, it binds systems together in a dynamic balance. One could poeticize that electrons orbit atomic nuclei, and in doing so, create the atoms that build everything tangible. It's orbiting that allows structure, so being in orbit is not a subservient act. It's a creative one that allows complex structures and stability. Without orbiting, without relationships of gravitation and revolution, the universe would be a diffuse, structureless haze. Likewise, in human existence, binding oneself to ideals, causes, or communities greater than oneself can give structure and meaning to life. We orbit principles of justice, love, or curiosity, and that orbit guides us and gives our journey shape. Standing under the night sky now, we no longer see moons as mere lights or dots. We see destinations that humans and our robotic envoys have touched. We also see stories. The moon is no longer just Apollo's goal, but Artemis's next foothold, and a muse for humanity's future. The moons of Jupiter are no longer just Galileo's tiny points. They are volcanic Io, oceanic Europa, massive Ganymede, ancient Callisto, each a world to marvel. We are connected to them now by knowledge and by the anticipation of discovery. When we behold Saturn through a telescope and spot Titan as a faint dot, we know there's an Earth like sky there, and perhaps we feel a kinship with whatever chemistry is brewing on its surface. In a sense, through exploration, all these moons have become extensions of our mental world. Our human story has expanded to include them. We've left footprints on one, tire tracks on another, probe markings on Titan's frozen ground. We've made these distant places, in some measure, part of our shared human experience. And as we did so, we found that those places were not barren in meaning. They reciprocated by teaching us about ourselves. They taught us patience, taught us humility, taught us unity. In mythology, the moon often represented the feminine, the cyclical, the responsive, complementing the sun's masculine, steady output in many cultures. One could say the moons of the solar system collectively represent the yin to the planet's yang, the supportive, nurturing side of planetary systems. They stir tides. They may nurture life in their oceans. They moderate axes and climates. And philosophically, maybe we as humanity play a moon-like role in relation to our planet, nurturing it by reflecting the light of knowledge and awareness onto it. We have the power to bring unconscious processes into consciousness and address them, much as the moon's light allows us to navigate the dark. Finally, consider the sheer beauty and improbability of it all. In a universe that may be mostly empty, here we are in a system with a wealth of moons, where one tiny rocky sphere can orbit a gas giant and harbor a subsurface sea that might host alien microbes, or where a dead-looking moon turns out to have cryovolcanoes that paint its surface. Is this not wondrous? It speaks to an inherent creativity in nature. In that, some find spiritual meaning, seeing in the proliferation of moons and their diverse stories a sort of cosmic art, an expression of what some might call the divine, or simply the boundless creativity of physics. The moons invite us to think about companionship and solitude. Our Earth's moon has been a constant companion, night after night. Mars's little moons accompany it like faithful, if odd, shaped pets. Jupiter carries an entire miniature solar system, a reminder that even in the company of others, each member can be distinct and vital. As we humans venture out, possibly one day establishing bases on the moon or visiting Mars, we too become companions to these moons, integrating ourselves into the cosmic neighborhood as participants, not mere observers. In closing our journey, we return to a simple scene, a person standing under a moonlit sky, gazing upward. Beyond the silhouette of our moon, our mind's eye knows there are other moons orbiting distant planets, shining in their skies. The night is richer now. We feel connected to something far beyond, as well as deeply rooted in our own world. The silent watchers of the night have shared with us their stories, and we find that they are our stories too. Stories of orbit and influence, of reflection and yearning. In their silent orbits, these moons, great and small, are indeed guardians of the night. They keep the stories of their planets and share their light with the darkness. As our journey ends, we look up with a deeper reverence. The night sky is alive with these silent companions, forever circling, forever reflecting. They inspire us to continue our cosmic dance of exploration, and under their watchful glow, we carry onward, seeking knowledge, seeking connection, and seeking our place among the stars. Cosmos. The word itself is like a soft whisper in the dark of night, inviting us to look up and wonder. Born from ancient Greek, it means order or ornament, the opposite of chaos, the adornment of the night sky. For as long as humans have had language, we have given a name to the grand scheme of everything. We have always stood under the starry vault, hearts beating with curiosity, minds aching to understand what it all means. In a silent desert or on a grassy hill, our ancestors gazed at the stars with awe. Tiny lights flickering in the vast darkness became stories, became gods and guides. Under that cosmic canopy, they felt small yet connected to something immense. They sensed in those pinpoints of light a pattern, a rhythm, seasons changing, moons waxing and waning, a cosmos moving with purpose. To say cosmos is to imply the universe is not a random scattering of matter, but a harmonious whole. Beyond the chaos of daily life lies a greater order we can barely fathom. When we whisper the word, we summon an ancient feeling, the awe of knowing we are part of a mysterious, breathing entirety. The cosmos has always beckoned us. It humbles us with its scale and age, yet it also comforts us with the idea that we belong to it. We have wondered if the twinkling lights had messages for us, if the sky was a story written in stars. Generation after generation, we pass down myths and measurements, trying to bring the heavens into human understanding. Through wonder and imagination, we wove ourselves into the fabric of the cosmos. Even now, in an age of bright cities and glowing screens, that old impulse remains. Go somewhere dark and clear and look up. The same Milky Way that dazed our ancestors arches overhead. In that band of light, millions of distant suns blurred together, we find both our history and our destiny. We feel the tug of an ancient question with each breath under the stars. What is all this? What does it mean that we live in a cosmos so vast and beautiful? From the earliest times, cosmos has meant more than just the physical universe. It carries a sense of profound order and connection. To reflect on the cosmos is to step beyond oneself, to see life on Earth as part of a larger story. It is to realize that the atoms in our bodies were born in stars, that our existence is tied to cosmic events beyond memory. It is to feel both tiny and tremendous, a fleeting moment, and an integral part of eternity. So let us meditate on that word and all it entails. Let us journey outward and backward, upward and inward. In this story of the cosmos, we will travel from ancient myths to modern science. We will seek patterns in the sky that guided our ancestors and follow the light of distant galaxies that reveal our cosmic origins. We will ponder forces unseen and marvel at galaxies strung like jewels on invisible threads. Through it all, we hold on to that childlike wonder that first taught us to say cosmos with reverence. Our voyage begins where it must, in the tales and dreams of those who first looked up and tried to understand. The cosmos has always been our mirror and our muse. In its vastness, we have found grand myths of creation, of gods and monsters, of order emerging from chaos. To truly know the cosmos, we start with the ancient stories written not on paper, but across the sky itself. The ancient cosmos. Before science, there were stories. In the cradle of civilization, human beings looked to the sky and saw a grand drama unfolding above. The cycle of night and day, the march of seasons, the wandering of planets among the stars. All these celestial motions cried out for explanation. And so our ancestors gave the cosmos a face, a script, a meaning. The ancient heavens became a mirror of life on Earth, a canvas on which they painted their hopes and fears. In ancient Egypt, each sunrise was not just a new day, but a victory of order over darkness. The sun was the god Ra, sailing across the sky in his brilliant boat. Every morning he was reborn in the east, bringing light and life. Every evening he descended into the underworld, battling forces of chaos to ensure the sun would rise again. To the Egyptians, the cosmos was upheld by these divine cycles. Ra's daily journey affirmed the rhythm of life, death, and renewal. The Nile would flood and recede, crops would grow and be harvested, just as surely as the sun would set and rise. Their myths gave cosmic meaning to earthly patterns, reassuring them that the universe was orderly and life-sustaining as long as the gods maintained balance. Far to the north, under Greek skies, people also sought cosmic order through myth. They imagined the night as a storybook opened overhead. Constellations were characters, a great hunter forever chasing a bull across the heavens, a hero carrying the weight of the sky on his shoulders, a queen enthroned among the stars. The Greeks looked up and saw legends. Orion with his shining belt of 3 stars, majestic and bold, the Great Bear lumbering around the North Pole, Andromeda chained to her stellar rock. Each constellation marked a tale of love or bravery or caution, a lesson twinkling from the firmament. Above all reigned Zeus, king of the gods, whose authority extended over both the sky and human affairs. The moving planets, the wanderers, were given names and personalities: fiery Ares, Mars; bright Aphrodite, Venus. By telling these tales, the Greeks found patterns in the stars, a cosmic order reflecting their own virtues and vices. The movement of the heavens hinted at divine plans. If Mars appeared red and bright, was Ares signaling war? If Venus rose in the evening, did Aphrodite bless lovers? In this ancient cosmos, the boundary between heaven and earth was thin, each influencing the other. Across the ocean in other lands, countless cultures wove their own cosmic tapestries. In old China, the night sky was envisioned as a celestial empire, mirroring the earthly one. The emperor was said to be the son of heaven, and the stars were arranged into palaces and provinces. The Chinese sky was divided into constellations, forming a meticulous heavenly bureaucracy. A comet streaking through the sky might be interpreted as a wayward official or a portent of change in the kingdom. An eclipse was not just an astronomical event, but a dragon devouring the sun or moon, a sign that the harmony of the cosmos had been disrupted. To restore balance, people gathered to beat drums and gongs, scaring the dragon away. When the sun returned, it reaffirmed the cosmic order and the emperor's mandate. Through such rituals and myths, the ancient Chinese made sense of celestial motions as reflections of moral and political order on Earth. In the Indian subcontinent, sages imagined a layered cosmos teeming with gods and avatars. The sky was the abode of deities riding the clouds. The sun was Surya, a radiant god who drove his chariot across the heavens, pulled by 7 horses, the colors of sunlight. The moon was Chandra, gentle and cool, gliding through the night. The planets were also gods, each with personality and power, collectively called the Navagraha. Indian cosmology spoke of a universe born from a cosmic egg, of endless cycles of creation and dissolution measured in kalpas, lasting billions of years, staggering spans of time encoded in myth. Yet these huge cycles tied into everyday life. The positions of planets could influence a person's destiny, the timing of rituals, the fortunes of kings. By observing the heavens, ancient Indians felt they could glimpse the divine rhythm that underpins reality, aligning their lives to the dance of the cosmos. No matter where on Earth, early peoples found ways to map the sky onto their own experience. The Babylonians meticulously tracked the movements of planets and stars and wove them into their myths of gods like Ishtar, Venus, and Marduk, Jupiter. They recorded eclipses and believed in cosmic omens, that a falling star could foretell the fall of a king. The Maya of Central America built observatories to follow the sun and Venus, timing agriculture and ceremonies to celestial cycles. For them, the cosmos was a ceaseless wheel of time, with each era ruled by different gods. Indigenous peoples of North America saw constellations as great hunters and animals, integrating the sky into storytelling and navigation. Every culture found its own cosmic North Star by which to guide human life. These ancient cosmologies differed in detail, but they shared a purpose: to make the vast, unknowable sky intimate and meaningful. By projecting stories onto the stars, our ancestors found comfort and guidance. The cosmos became a grand clock and calendar, its motions providing a sense of predictability in an uncertain world. The rising of Sirius just before dawn signaled the Nile's flood, and thus renewal, to the Egyptians. The appearance of the Pleiades in spring told Greek sailors that sailing season had arrived. The heavens and earth were interwoven in a tapestry of sign and story. Most importantly, the ancient myths gave people a sense of belonging in a huge universe. If the heavens were populated by gods and heroes, then human life was part of that divine drama. Nothing was random. The cosmos had intention, personality, narrative. A shooting star could be a departing soul. The Milky Way could be the spilled milk of a goddess or the bridge to the afterlife. By aligning with these cosmic stories, performing rituals at solstices, building temples to face sunrise, tracing the planet's paths, ancient humans felt they were participants in the cosmos, not mere spectators. In those early nights under open skies, the cosmos was both guide and canvas. People drew connections between the circling stars and the cycles of their own lives. Birth, death, love, conflict, harvest and drought, all found reflection in the movements above. The myths may not have been scientifically accurate, but they were true in a deeper sense. They captured the emotional truth of being human in a vast and mysterious universe. They helped us navigate not just by land or sea, but through the uncharted waters of existence. Thus, the ancient cosmos was a place of narrative and meaning. It was alive with motion and intention. Every sunrise was a story, every eclipse a warning or wonder, every constellation a reminder that we are part of something greater. With these stories, humanity's long conversation with the stars began. Over millennia, those conversations led to patterns noted, calculations made, and the first whispers of a new approach to understanding the cosmos. Myth would eventually inspire measurement, and storytelling would lead to science. As our methods changed, the goal remained the same: to find our place in the grand order of the cosmos and to ensure that the cosmos made sense. The birth of the modern cosmos. For thousands of years, the Earth sat proudly at the center of the known universe in human imagination. It seemed obvious. The ground beneath us felt still and solid, while the heavens whirled around. The sun rose in the east, journeyed overhead, and set in the west, surely circling us. The stars rotated nightly around the North Star, as if painted on the inside of a celestial dome with Earth at its core. This geocentric cosmos, codified by philosophers like Aristotle and Ptolemy, was cozy and reassuring. Humanity lived at the heart of creation, the focal point of God's plan or nature's design. Above, the crystal spheres turned in orderly concentric circles, carrying the sun, moon, planets, and stars in divine choreography. In this model, the cosmos was finite, well-ordered, and centered on us. But whispers of a different truth had long existed. As early as ancient Greece, a few bold thinkers, like Aristarchus, suggested that the Earth might move around the sun. This idea was largely dismissed or forgotten for centuries. It simply felt wrong. How could Earth be moving? We felt no incessant wind from such motion, no constant shaking. And if Earth swung around the sun, where was the parallax in the stars, the tiny shift in star positions that such motion should produce? None could be seen with the naked eye. So the geocentric view held sway through antiquity and the Middle Ages. Then, in the 16th century, a Polish astronomer named Nicholas Copernicus quietly revolutionized our view of the cosmos. He proposed a bold simplification. Suppose the sun is at the center, and the Earth is just another planet circling it. In one stroke, the cosmic order could be explained more elegantly. The retrograde loops of Mars in the sky, the cycles of Venus, all made sense if Earth was moving too. Copernicus published his heliocentric theory in 1543, carefully dedicating it to the Pope and couching it as a mathematical convenience. Yet the implication was clear. Our planet was not the pivot of creation. It was a radical leap, met with skepticism or silence by most contemporaries. After all, it upended common sense and challenged religious doctrine. But the seed of the modern cosmos was planted. It would take brave observers and thinkers to make that seed sprout. Early in the 17th century, Galileo Galilei in Italy heard of a new invention, the telescope. He crafted his own and pointed it at the night sky, becoming the first human to see certain wonders. Through Galileo's telescope, the moon revealed mountains and craters. Not the perfect heavenly orb philosophers imagined. Jupiter appeared as a tiny disk, accompanied by 4 points of light that moved, Jupiter's moons, orbiting not Earth but Jupiter itself. It was a celestial ballet defying geocentric dogma. Here were objects clearly circling a world other than our own. Galileo also observed Venus showing phases like the moon, a behavior only possible if Venus circled the sun, not Earth. Star clusters in the Milky Way resolved into countless faint stars, suggesting the cosmos was far larger and richer than assumed. With each observation, Galileo dealt blow after blow to the Earth-centered model. He wrote of his findings, championing the Copernican sun-centered system. This earned him admiration among some and condemnation from others. The idea that Earth moved was still too great a heresy for many. Galileo famously faced the Roman Inquisition and was forced to recant. But the truth was out. Our world was not the fixed center. Earth was a planet in the heavens, one among several. With the heliocentric model gaining evidence, the cosmic stage expanded. Johannes Kepler refined the picture,
by discovering that planets travel in ellipses, not perfect circles, and speed up and slow down in their orbits according to precise laws. It was as if the cosmos had its own music, and Kepler had begun to hear its rhythm in the data. Shortly after, Isaac Newton in England provided the masterstroke. He formulated the law of universal gravitation, showing that the same force pulling an apple to the ground keeps the moon circling Earth and Earth circling the sun. In Newton's new universe, the celestial and terrestrial were unified. The heavens were not held up by crystal spheres or angelic powers, but by gravity, an invisible thread binding planets to stars. Suddenly, the cosmos became a mechanistic marvel, a grand clockwork governed by laws that could be understood and even predicted by humans. The music of the spheres was transcribed into mathematics. The modern scientific cosmos was being born, and in it, Earth was merely one cog in a vast machine. As the centuries turned, our understanding leapt forward. By the 19th century, astronomers realized the sun itself was not the center of all creation, but rather the center of a local family of planets. The stars, once thought to be distant lanterns or holes in the firmament, were confirmed to be other suns scattered across unimaginable distances. The night sky, which to the ancients was a fixed dome, became an ocean of stars in 3 dimensions. We measured the first distances to stars and found them stupefyingly far. The nearest, Alpha Centauri, is over 4 light-years away, 40 trillion kilometers. The absence of observed parallax now made sense. The stars were vastly farther than imagined in Aristotle's time, so their parallax was tiny. Our sun was thus not the center of all stars, but just one star drifting in a great starry city. That starry city is the Milky Way galaxy, a broad band of light wrapping the sky. In the early 20th century, astronomers pieced together that the Milky Way was an immense disk of hundreds of billions of stars. Our sun lay not at the center of this disk, but off to the side in a spiral arm, a suburban star in the galaxy's outskirts. We had been demoted once again from center of the universe to mere resident of one galaxy among possibly many. Yet even then, many believed the Milky Way was the entirety of the universe, an island universe surrounded by a void. Reality had another plot twist in store. In 1920, astronomers Shapley and Curtis engaged in the great debate over the scale of the universe, arguing whether spiral nebulae, like Andromeda, were part of the Milky Way or distant galaxies of their own. This question was settled in the mid-1920s when Edwin Hubble, using the giant Mount Wilson telescope, observed stars in the Andromeda Nebula. He identified particular stars called Cepheid variables, whose blinking rhythm allowed him to calculate their distance. The result was staggering. Andromeda was far outside our Milky Way, a galaxy in its own right. In one announcement, Hubble shattered the confines of our known cosmos. The universe was vastly larger than we had imagined. The Milky Way was but one galaxy among billions spread throughout space. As if that weren't enough, Hubble soon discovered that these galaxies are flying apart from each other. Space itself is stretching. The spectra of distant galaxies were shifted toward the red, like the lowered pitch of a receding siren, indicating they were rushing away. The farther the galaxy, the faster it fled. It was as though the cosmic fabric were inflating, carrying galaxies apart like driftwood on a rising tide. The implication was profound. If you rewind this expansion, there was a time when everything was closer together, perhaps a moment when the entire universe was a single point. The static, eternal cosmos of old gave way to a cosmos with a dynamic history, a beginning, what we now call the Big Bang, and perhaps an end. Thus, in just a few centuries, our cosmic understanding transformed utterly. We went from a cozy Earth-centered bowl of stars to an immense, law-governed expanse where Earth is a moving planet, the Sun a modest star, the Milky Way one galaxy among a multitude, and the universe itself expanding and evolving. Each step was a blow to human vanity, but a boon to human knowledge. With each step, the cosmos grew grander and more mysterious, yet also more knowable through science. The modern cosmos was not built in a day. It emerged gradually as old theories shattered and new discoveries took their place. It required curiosity, courage, and the willingness to accept that our intuitions can be wrong, that reality may be far stranger and more magnificent than our ancestors ever dreamed. By embracing a sun-centered system, by mapping the Milky Way, by discovering galaxies beyond our own, humanity experienced a kind of cosmic rebirth. We shed ancient illusions and stepped into a wider universe, guided by observation and reason. And as the scale of the cosmos expanded, so did our sense of wonder. The night sky, once a fixed storybook of constellations, became an endless frontier. We now knew that when we gaze at the Milky Way, we peer into the heart of our galaxy, and when we spot the faint smudge of Andromeda, we behold a sister galaxy 2.5 million light-years away. The light entering our eyes left that galaxy before our species existed. The modern cosmos is vast, full of galaxies drifting in the darkness, all governed by the same natural laws.
This was a cosmos that could be analyzed with telescopes and equations, but it still evoked awe. In fact, the more we discovered, the more profound and humbling the mystery became. Having found our true place, not the center, but part of a cosmic community of worlds, we were ready to explore what this newfound universe looked like. With minds freed from the confines of geocentrism, and with ever more powerful tools, we set out to observe the cosmos in all its glory. The next step of our journey would be to truly behold the universe with new eyes, to collect the ancient light of stars and galaxies, and from it, read the story of time itself.
The observable cosmos. Armed with newfound knowledge and powerful eyes, humanity set out to truly see the cosmos. What had been mysterious points of light became tangible suns and galaxies through the lens of the telescope. Our curiosity, once limited by human sight, now leapt forward with each improvement in our instruments. The cosmos opened like a book under a magnifying glass, revealing detail upon detail written in light. We learned a startling fact. To observe the universe is to look back in time, for light takes time to travel. Consider the starlight reaching us tonight. The nearest star beyond our sun, Proxima Centauri, lies 4.24 light-years away. The light hitting our eyes from that star left it over 4 years ago, crossing trillions of kilometers of space before gently landing on our retina. We see Proxima Centauri not as it is now, but as it was 4 years in the past. And that's our nearest neighbor. Sirius, the brightest nighttime star, shines 8.6 light-years away. We see it as it was about when the last decade began. The North Star, Polaris, is 433 light-years distant, so the light-guiding sailors tonight set off around the time Galileo first pointed a telescope skyward. With every step up in distance, we peer further back in time. The Andromeda Galaxy, faintly visible as a smudge, is over 2 million light-years away. When its light began its journey, early hominins on Earth were chipping stone tools. This realization transformed the night sky into a kind of cosmic history book. Telescopes became our time machines, collecting ancient photons that have been traveling for eons. By capturing this light and studying it, we decode stories from long ago and far away. The color and brightness of a star's light tells us its composition and temperature. The Doppler shift of a galaxy's light reveals its motion through space. When we see the glittering band of the Milky Way, we now understand it as the combined glow of billions of stars, many whose light has traveled tens of thousands of years to reach us. To look out is to look back. As telescopes grew in size and sophistication, the depths of the observable cosmos unfolded. In the 19th century, astronomers with new refractors and reflectors
saw that some fuzzy patches of light, nebulae, had spiral shapes. They suspected these might be island universes, galaxies outside our own, later confirmed by Hubble. Each advance in observational power was like opening a new window in our cosmic house, offering a view further into space, and thus further into the past. In the 20th century, we launched telescopes above the blurring veil of Earth's atmosphere. The Hubble Space Telescope, deployed in 1990, proved transformative. Free from atmospheric distortion, Hubble could stare deeper into space than any instrument before. In 1995, astronomers did a daring experiment. They pointed Hubble at a seemingly empty, dark patch of sky near the Big Dipper, where no known stars or galaxies were visible, a speck of sky no bigger than a grain of sand held at arm's length. They let Hubble's camera soak in light for 10 straight days. What came back was a revelation: the now famous Hubble Deep Field image. Far from empty, that little patch of darkness was overflowing with nearly 3,000 galaxies, of all shapes, sizes, and colors, each a swarm of billions of stars. Some were relatively nearby, but many were incredibly distant, their light having traveled for billions of years. In those dim smudges, Hubble had captured galaxies as they were when the universe was young, cosmic baby pictures, just a few billion years after the Big Bang. That single image was like a core sample of the universe, drilling down through cosmic time. It showed a universe teeming with galaxies, even in a tiny, unremarkable bit of sky. Later, Hubble gazed even longer and deeper, producing the ultra-deep field in 2004, and then the extreme deep field in 2012, revealing galaxies more than 13 billion years in the past, when the first galaxies were just emerging. In the Hubble ultra-deep field, almost every point of light is an entire galaxy. Some are seen as they were only 400–800 million years after the Big Bang, full of newborn stars. By looking far away, we looked back to a time when the universe was young. Every telescope, whether a backyard amateur's or a great observatory in space, is fundamentally a light collector. It gathers the sparse, ancient photons that rain down on us, focusing them into an image or feeding them to instruments that can analyze their secrets. Through visible light telescopes, we see stars and galaxies as our eyes would, only fainter and farther. Through radio telescopes, we tune in to the whisper of the cosmos at long wavelengths, the songs of cold hydrogen clouds and the ghostly crackle of remnant radiation from the Big Bang. Infrared telescopes peer through cosmic dust to find stars being born in swaddling nebulae and detect the faint glow of the most distant galaxies, whose light has been stretched to infrared by the expanding universe. Ultraviolet and X-ray telescopes capture high-energy phenomena, flares on stars, the glow of gas around black holes, the hot plasma in galaxy clusters. Each portion of the electromagnetic spectrum is like a different chapter of the cosmic story, and we've learned to read them all. The observable cosmos extends far beyond what human eyes alone can see, thanks to these extensions of our senses. Perhaps the most ancient light of all that we have observed is the cosmic microwave background, the cooled, faint afterglow of the Big Bang itself. Discovered by accident in 1965 as a pervasive microwave hiss in a radio antenna, this all-sky glow is the light from about 380,000 years after the Big Bang, when the hot plasma of the early universe finally cooled enough to become transparent and release photons in all directions. We see it now as a uniform microwave glow coming from every direction, just a few degrees above absolute zero, the oldest fossil of light, nearly 13.8 billion years old. Detailed maps of the microwave background made by satellites, COBE, WMAP, Planck, show it's mostly uniform, but with tiny variations in temperature, the seeds of all future cosmic structure. This is literally a baby picture of the universe, long before stars or galaxies existed. It's a reminder that our telescopes have pushed our vision to its limit. We can nearly see the Big Bang itself. Within the observable cosmos, we have catalogued wonders beyond count. We've seen star clusters,
with hundreds of thousands of suns, nebulae that are stellar nurseries sculpted by winds and radiation, galaxies colliding and merging in dances that last hundreds of millions of years. We have detected planets around other stars by the subtle dimming of starlight or the wobble of spectral lines. We now know planets are common, numbering in the billions in our galaxy alone, from hot Jupiters skimming their stars to Earth-like rocks in temperate orbits. We've measured the universe's expansion and even glimpsed its acceleration due to an enigmatic, dark energy. All of these achievements flow from extending our senses with instruments and collecting the light, or other radiation, that streams through space, carrying messages from afar. Telescopes, in a poetic sense, gave the universe a voice in time. Through them, we listen to the echoes of the past. When we look at a distant galaxy cluster, we might be seeing it as it was when our own sun had not yet formed. In the faint glow of a red-shifted galaxy, we might be witnessing an event that occurred shortly after the dawn of time. The observable cosmos is a time capsule cosmos. The phrase observable universe also reminds us of limits. Light from extremely distant regions hasn't had time to reach us in the 13.8 billion years since the Big Bang, so there are horizons we cannot see beyond, at least not yet and maybe not ever, if the expansion accelerates. This doesn't mean those regions don't exist, just that they lie beyond our view. So the observable cosmos, everything we can see or detect, is still potentially only a piece of a larger whole. But it is grand enough, about 93 billion light-years across today, accounting for expansion, containing perhaps 2 trillion galaxies. Each of those galaxies, in turn, contains billions or trillions of stars, and around many of those stars orbit worlds we are only beginning to discover. Looking up from Earth, a small creature on a small planet, we now can perceive structures and events on scales our ancestors never imagined. We have essentially pulled back the curtain of distance, and what we found is a universe that is dynamic and changing. The sky is no longer a fixed backdrop, it is a living history. Every point of light is a story unfolding. Some star being born in a nebula, another nearing its death as a red giant, a galaxy swirling in a gravitational dance with a neighbor, a supernova shining briefly like a cosmic firework. We catch these events mid-stride, like reading random pages from a vast novel. Telescopes allowed us to no longer be passive inhabitants of the cosmos, but active witnesses to its grand story. Each night an observatory opens its dome and points its giant eye outward. We extend our reach farther in space and further back in time. We do this not for conquest, but for understanding, to fill in the chapters of the cosmic story from the beginning until now. And through these observations, we have come to see the universe not as static, but as an unfolding tale with a beginning, middle, and ongoing narrative. Having surveyed what we can see, the stars and galaxies and background glow, we noticed a grand pattern in how matter is arranged on the largest scales. Galaxies are not scattered randomly. They form a vast cosmic web of filaments and voids. To this we now turn, the large-scale structure of the universe, the cosmic web that gravity built, seeded by tiny quantum ripples from the dawn of time. The cosmic web. On the grandest scales, the universe is organized into a vast cosmic web, a structure both simple and intricate, like lace stretching across unimaginable distances. If we could zoom way, way out beyond our galaxy, clusters of galaxies would begin to outline a pattern. Galaxies are not evenly sprinkled through space, but collected in filaments, sheets, and dense knots, clusters, with huge voids between them where few galaxies reside. The cosmos, viewed from afar, resembles a web or sponge, bright threads and nodes of matter surrounding dark, empty bubbles. Gravity is the master architect of this cosmic web. Over billions of years, gravity drew matter together, amplifying tiny primordial irregularities into the vast structures we see now. In the early universe, matter was nearly uniform, with slight denser spots here and there, imprinted as those tiny temperature ripples in the cosmic microwave background. As the universe expanded and cooled, these denser spots, seeded by quantum fluctuations and stretched by inflation, exerted a bit more gravitational pull, drawing in surrounding gas and dark matter. Over time, the slightly denser regions grew into filaments and clumps. The empty regions gave up matter to the crowded ones and became enormous voids. Imagine flying through a slice of the universe a few billion light-years across. For millions of light-years, you might see almost nothing, traversing a void where only the occasional dim galaxy or wisp of hydrogen appears. Then, ahead, you'd see a filamental chain of galaxies stretching across space like a gossamer strand. Drawing closer, that filament resolves. It's a chain of galaxy clusters connected by thinner tendrils of galaxies. You follow the filament to a nexus, a rich cluster of galaxies where filaments intersect, perhaps like the Coma cluster containing thousands of galaxies swarming around a common center. From that hub, multiple filaments radiate out, each leading to other clusters. This is the cosmic web: clusters, nodes, connected by filaments, separated by voids. It's akin to the structure of a sponge or foam, an interlocking network of walls and channels. Our own Milky Way lies within this web. It is part of a small cluster, the local group, which in turn is on the outskirts of a larger Virgo cluster. That cluster is part of a filament that stretches toward the Great Coma cluster. In fact, astronomers have mapped our local section of the cosmic web and found that our local group, Virgo cluster, and other nearby clusters are all part of a supercluster system they've named Laniakea, Hawaiian for immeasurable heaven. Gravity is drawing our local group, including the Milky Way and Andromeda, toward the Virgo cluster, and all of Virgo and its neighbors toward an even larger concentration called the Great Attractor. Our galaxy, in the far future, will drift along the web into those larger structures, though perhaps not before dark energy's expansion halts that motion, an evolving contest between expansion and gravity. One of the striking things about the cosmic web is how empty the voids are. Some voids span hundreds of millions of light-years with almost no galaxies. In contrast, the filaments and clusters are crowded. In massive clusters, galaxies can be just tens of thousands of light-years apart, very close in cosmic terms, and space between them is filled with hot, X-ray emitting gas, heated by the gravity of the cluster. The filaments themselves contain not just the galaxies we see, but also lots of dark matter and diffuse gas connecting cluster to cluster. In fact, simulations and observations suggest that most of the ordinary matter, atoms in the universe, resides not in galaxies, but in the filamentary tendrils of warm, hot intergalactic medium, WIM, threading the voids. It's like an invisible scaffold. The galaxies are like dewdrops on a spider web, outlining it, but much of the web itself is faint and hard to see directly, composed of thin gas and especially dark matter. Dark matter, that mysterious substance making up about 85% of the matter in the universe, is the backbone of the cosmic web. While ordinary gas can radiate energy and settle, dark matter does not radiate, so it forms large, diffuse halos. It was dark matter that first clumped due to gravity, with ordinary matter later falling into the gravitational wells the dark matter created. In supercomputer simulations of cosmic structure formation, one starts with a nearly uniform distribution of dark matter, with tiny random density fluctuations, and lets gravity work over billions of years. The result is a filamentary network, extremely similar to what large galaxy surveys observe. The bright nodes in such simulations correspond to where clusters of dark matter, and later galaxies, form. The long dark strands correspond to filaments of dark matter along which galaxies and clusters align. The empty regions correspond to voids evacuated of matter. It's a beautiful example of emergent order. Out of near uniformity emerges complexity, a cosmic web, simply from the action of gravity over time. Tiny fluctuations in density, originating from quantum jitters in the infant universe, became the template for everything. Stars, galaxies, clusters, the web. The cosmic web is the largest pattern we know. It shows that on the grandest scales, the universe has a structure, homogeneous and isotropic, only when averaged over truly enormous volumes, but locally clumpy in a sponge-like way. It's often said that the universe on very large scales looks the same everywhere, the cosmological principle. And it's true that if you average over hundreds of millions of light years, one region is much like another in terms of galaxy counts. But zoom in a little less and the web stands out. Homogeneous only in a statistical sense, but in reality, threaded and bubbled. It's intriguing to note parallels between the cosmic web and other networks. The distribution of matter in the universe, as revealed by galaxy surveys like the Sloan Digital Sky Survey, bears a resemblance to the neural networks in brains, or the large-scale structure of the internet. Hubs and spokes, clustering of connections. This might just be a coincidence of pattern. Nature finds similar solutions to connectivity problems, or possibly a hint of deep universal principles of self-organization. When scientists compared the network properties of the cosmic web and the network of neurons in a brain, they found tantalizingly similar complexity and distribution despite the difference in scale by 27 orders of magnitude. It's a reminder that simple laws, like gravity's inverse square attraction and expansion of space, can create intricate structures mirrored elsewhere in nature. Crucially, the cosmic web is not static. It's still evolving. Over time, gravity will continue pulling matter along filaments into clusters. The rich get richer, clusters accumulate mass, and the voids get emptier. Superclusters may merge into even larger structures, sometimes called hyperclusters, though there's a limit. Eventually, dark energy's accelerated expansion will push galaxies away from each other faster than gravity can overcome. It's thought that in the far future, 100 billion years or more, distant clusters will recede beyond our observable horizon, effectively isolating each remaining cluster or group as its own island universe. At that point, any cosmic web structure beyond our local cluster will be unobservable. The larger pattern will be lost to view, though it will still exist beyond our reach. For now, however, we live at a time where we can map the cosmic web, see its glory, and use it to test our theories of cosmology. Understanding the cosmic web helps answer profound questions. How did the universe transition from the near-uniform fireball after the Big Bang to the rich hierarchy of structure we see now? The answer: the interplay of gravity, pulling matter into structure, and expansion, spreading things out, created a foam-like arrangement. Tiny fluctuations grew to filaments, matter flowed like rivers into cluster basins, and vast quiet voids were left where nothing much happens. Having journeyed from our planet to the galaxy, to clusters and the cosmic web, we've framed the large-scale architecture of the cosmos. But what holds this architecture together, and what threads run through every level of this tapestry? For that, we must discuss the fundamental forces and fields: gravity, electromagnetism, and the nuclear forces, the hidden framework, underlying movement and structure everywhere in the cosmos. Forces and fields. In the grand ballet of the cosmos, 4 fundamental forces choreograph every move. They are the unseen influences that shape everything from the orbits of planets to the light in our lamps to the fusion in stars. Though invisible, they form a hidden framework that makes the universe dance. Each force is like a different instrument in an orchestra, and together they compose the music of the cosmos, from the smallest scales to the largest. Gravity is the most familiar, and yet in many ways, the most mysterious. It is the sculptor of the cosmos, the gentle but persistent pull that guided matter into spheres and orbits. Every time an apple falls from a tree, or we feel our own weight, we are feeling gravity. This same force reaches across the emptiness of space to keep the moon circling Earth and Earth circling the sun. It binds solar systems and steers stars around the centers of galaxies. It gathered galaxies into clusters along the cosmic web. Gravity is by far the weakest of the four forces on small scales. A tiny magnet can lift a paperclip against the entire Earth's gravity. But over large scales it dominates because it only attracts and never cancels out. Over time, its tiny tug accumulates into an inexorable current that builds structure. Einstein revealed that gravity is not a force in the traditional sense, but a curvature of space-time itself. Mass and energy bend the fabric of space and time, and objects move along those curves. The sun dents space-time, and Earth rolls around that dent like a marble in a bowl. This elegant understanding tells us gravity is the shape of the cosmos's geometry. It's what gives the universe its large-scale structure, what makes a cloud of gas collapse into a star, what pins us to our beloved Earth. Gravity is both patient and powerful. Given enough time, it can gather raw matter into galaxies or crush a star into a black hole. Largely, though, gravity is the quiet, persistent heartbeat of the cosmos, keeping worlds in their courses and the celestial architecture intact. Electromagnetism is the artist and communicator of the universe. It is the force responsible for light itself. Every beam of starlight traveling to our eyes is an electromagnetic wave. It also binds atoms and molecules. It's the reason you do not fall through the floor. The electrons in your shoes repel the electrons in the floor. Electromagnetism is vastly stronger than gravity at small scales. It's what makes magnets cling and lightning crackle, what lets compasses point north and radio waves carry music. In atoms, the electromagnetic force binds negatively charged electrons to positively charged nuclei, forming atoms. It causes atoms to link into molecules by sharing electrons, giving us the variety of chemistry. The warmth you feel from sunlight, the colors of a rainbow, the glow of a distant galaxy, all delivered by electromagnetic radiation. Unlike gravity, which only pulls, electromagnetism can both attract and repel. Opposite charges attract, like charges repel. This push-pull interplay creates structure on the atomic and human scales. It keeps electrons whizzing around nuclei instead of flying away, and it causes molecules to have the shapes they do, enabling the complex chemistry of life. In the cosmos, electromagnetism governs the behavior of plasma, the hot, charged gas found in stars and nebula. It sculpts the beautiful filaments of glowing gas in nebulae and the majestic arcs of solar flares rising from the sun. When we see the auroras dancing near Earth's poles, that's electromagnetism at play. Charged particles from the sun guided by Earth's magnetic field into the upper atmosphere, causing molecules to glow. Electromagnetic fields fill space around planets and stars. For instance, the sun's magnetic field, carried by the solar wind, creates a protective heliosphere around our solar system. On Earth, the electromagnetic force is the foundation of technology, electricity, electronics, wireless signals, and biology, chemical bonds, nerve impulses. In a cosmic sense, if gravity is the weaver of the cosmic tapestry, electromagnetism provides the vibrant colors and textures. It gives matter structure and allows the universe to be visible and radiant. The strong nuclear force is the powerful glue of the atomic nucleus. Working at tiny scales, the size of an atomic nucleus or smaller, it binds protons and neutrons together despite the electromagnetic force trying to push positively charged protons apart. Protons naturally repel each other strongly, since like charges repel, and within a nucleus, they are extremely close. It is the strong force that acts like cement to hold these protons and neutrons tightly bound. It is the strongest of the four forces in terms of raw strength, but it operates only across minuscule distances, about the diameter of a proton. Beyond that, its influence drops virtually to zero. Think of it as Velcro that sticks only at very close range. This is fortunate. If the strong force had longer reach, every atom might glom together into one giant nucleus. If it were weaker, nuclei heavier than hydrogen, which contain multiple protons, would fly apart, and the diversity of elements would vanish. In the cores of stars, when temperatures and pressures slam protons together with tremendous force, the strong force takes hold and fuses them. Hydrogen nuclei merge into helium, releasing tremendous energy. This nuclear fusion, governed by the strong force overcoming electromagnetic repulsion, is what makes stars shine for billions of years, converting a bit of mass to energy via EXMC2. The sunlight that warms your face is a byproduct of the strong force at work in the sun's heart, forging helium and releasing energy. Later, in a massive star's life, the strong force will operate on heavier elements. Carbon fuses into heavier elements all the way up to iron. But iron is the end of the line. Fusing iron doesn't yield energy, so in the final moments of a massive star, when its core is iron, the outward pressure stops and gravity causes collapse. The core implodes until the strong force between nucleons, protons, neutrons, and quantum pressures of neutrons say no further, either halting collapse and producing a neutron star, or if the star is massive enough, even the strong force yields and a black hole forms. In either case, the star's outer layers explode in a supernova, scattering heavy elements into space. The strong force in those violent moments forged all elements heavier than iron, gold, uranium, etc., which seed future stars and planets. Thus, the strong force is the creator of elements. It stitched the carbon in your cells, the oxygen in your water, the iron in your blood. Aptly named, it is stronger than electromagnetism at short range, for it must be to bind the nucleus. But outside the nucleus, we never directly sense it. It's confined to the tiny atomic realm. It's the secret fire at the center of matter, unleashed only in rare moments like inside a star or a nuclear reactor or bomb. Without the strong force, atoms beyond hydrogen wouldn't hold together, and the cosmos would be a featureless fog of particles. With it, the richness of atomic matter exists. The weak nuclear force is the most subtle and elusive of the four. It operates within atomic nuclei as well, responsible for certain kinds of nuclear transformations. In particular, it governs radioactive decay and the conversion of one type of particle into another. The weak force is the force of change. Where the strong force holds nuclei together, the weak force lets them transmute. For example, the weak force can turn a neutron into a proton, an electron, and an antineutrino. This is beta decay. This happens in naturally radioactive elements, like a carbon-14 atom decaying into nitrogen-14, emitting an electron. It also happens in the sun. In the proton-proton fusion chain, two protons fuse, and one must turn into a neutron via the weak interaction, allowing them to form deuterium, heavy hydrogen. Without that step, the sun's primary fusion cycle would stall. Thus the weak force, though feeble, is crucial. It lights the stars by enabling fusion and shapes the decay of heavy elements that heat Earth's interior. Radioactive decays of uranium, thorium, potassium contribute to Earth's geothermal heat, driving plate tectonics and volcanoes. The weak force has an incredibly short range, even shorter than the strong force, and is aptly named. It's far weaker than electromagnetism and strong force, stronger than gravity on subatomic scales, but gravity is irrelevant there. We typically notice the weak force only through radioactive decays or in high-energy particle physics experiments. It's carried by heavy W and Z bosons. It doesn't create binding structures. Instead, it allows particles to change identity. It is unique in that it can change a quark's flavor, turning a down quark to an up quark or vice versa, which is how a neutron becomes a proton. We rarely sense the weak force in daily life. It's a behind-the-scenes presence.
but it's essential for the evolving cosmos. Without it, the sun wouldn't shine the way it does, and many elements produced in supernovae wouldn't form, because beta decays during those explosions create elements like gold from lighter ones. If the strong force is the builder and electromagnetism the artist, the weak force is the quiet facilitator of change, enabling the cosmic alchemy that gives variety to matter. These four forces together form the infrastructure of reality. Each has its domain of influence. Gravity dominates the astronomical realm of planets, stars, and galaxies. Electromagnetism rules atoms, chemistry, and everyday phenomena. The strong force governs the atomic nucleus and powers stars. The weak force allows the transmutations that underlie both star power and natural radioactivity. They are the threads running through the cosmic fabric, and the fields they generate fill the space around us. Modern physics describes forces via fields and exchange particles. The gravitational field, possibly with gravitons. The electromagnetic field, carried by photons. The strong force field, carried by gluons binding quarks. The weak force field, carried by W and Z bosons. But leaving such technicalities aside, what's astonishing is that these few interactions explain a vast range of phenomena. Consider how these forces all play together in a simple moment. You stand outside on a sunny day. Gravity roots you to Earth and holds our planet in orbit around the sun. Electromagnetism governs the sunlight warming your face and lets your eyes see the world in color. It also keeps the ground solid beneath your feet, electrostatic repulsion between atoms. The strong force long ago fueled the nuclear reactions that produce that sunlight, and even now holds the nuclei of your atoms together. The weak force within the sun allowed protons to turn into neutrons, ensuring the fusion cycle could proceed steadily and power the sunlight. In your body, the weak force is causing a handful of potassium-40 atoms to decay each second, emitting neutrinos that stream harmlessly into space. In that one moment, all four forces are at work seamlessly, and you remain blissfully unaware, simply enjoying the warmth. Throughout cosmic history, these forces guided the formation of structure and the dynamics of change. Gravity drew together the cosmic web and formed stars and galaxies. Electromagnetism made those stars shine and binds atoms into molecules, leading to planets and life. Within stars, the strong and weak forces together forge new elements, which are then spread by supernovae to seed planets and life. We often call them forces of nature, but one might also call them cosmic rules or fundamental interactions, the basic ways pieces of the universe interact. Understanding these forces has allowed us to deepen our comprehension of the cosmos and harness aspects of it for our use. They also inspire a sense of marvel, how elegant that four simple interactions underlie the complexity of the entire universe. Gravity, shaping a galaxy cluster or light from a quasar, 12 billion light-years away, traveling to Hubble's mirror. It's all governed by the same physics that dictates an apple falling or a magnet sticking on a fridge. It suggests a profound unity that from the smallest scales of quarks to the largest scales of galaxy superclusters, the same fundamental forces operate, just with different relative strengths and effects. There are moments in modern physics where we dream of an even more unified picture. Perhaps these four forces were once one, a single force in the extremely hot young universe that later split into four distinct facets as the cosmos cooled. This is the idea behind grand unified theories and attempts to include gravity in quantum theory. Whether nature has such a unified force or not, what stands is that from the grandest cluster of galaxies down to the tiniest atomic nucleus, these four interactions suffice to explain what we observe. When you watch the stars at night, their light reaching you is an interplay of gravity, holding those stars together, and electromagnetism, bringing their light to your eyes, and even quantum effects of atoms, allowed by electromagnetic and strong forces. These forces are the invisible poetry of the cosmos. They make the silent emptiness of space a dynamic arena.
Through them, a universe that could have been chaos becomes a symphony of structure and motion. As we understand these forces, we appreciate the finely tuned balance that allows complexity to emerge. With gravity alone, matter would clump infinitely, or not form structure if universe expands too fast. Without gravity, no stars or planets would gather. Without electromagnetism, no atoms or light. Without strong force, no nuclei beyond hydrogen. Without weak, no stellar alchemy creating diverse elements. Our cosmos manages to have them all in just the right mix to give rise to the rich tapestry we see, including us, observers who can reflect on it. Armed with knowledge of the forces, we can now tell the stories governed by them. The deep time tales of stars and galaxies, their births and deaths. These will be our next focus, to see how the cosmos changes over time, how stars live and die, how galaxies evolve, and what fate awaits the universe. Time is the stage on which the forces play, and entropy, the tendency toward disorder, provides an arrow to that time. Let us now unfold the saga of deep time, witnessing the life cycles of stars and the evolving cosmos, told not in equations, but in emotions, as we connect to these distant events that ultimately made our own existence possible. Deep time. In the vast ocean of time, stars are born and die like living things. Galaxies grow and change, and even black holes have life stories. To truly grasp the enormity of cosmic history, we must step outside the human sense of time and enter epochs that dwarf our imagination. Deep time is a realm where 1,000,000 years might pass in the blink of an eye, where the dance of creation and destruction unfolds over eons, with a grandeur at once awe-inspiring and poignant. The life of a star. Picture a dark nebula in a spiral arm of the Milky Way, a cold, dusty cloud light years across, quietly drifting for ages. Within it, a subtle gathering begins, perhaps the shockwave of an ancient supernova, or the pressure of a spiral density wave triggers parts of the cloud to contract under gravity. In those shrinking pockets, gas and dust draw together, atoms crowd and collide, heating up. What was cold and dark starts to glow dull red from the heat of compression. In one such cocoon, at the center of the collapsing cloud, a new light ignites. A protostar is born. It's like a baby star, unstable, convulsing with magnetic storms, gobbling up gas from the surrounding cloud. As it grows, its core becomes denser and hotter until one miraculous moment, hydrogen atoms, squeezed and heated fiercely, begin to fuse into helium. The strong force binds them, the weak force facilitates the fusion, and a torrent of energy is released. Outward pressure from this nuclear fire balances the inward crush of gravity. The star settles into a stable rhythm. It has entered the long, middle chapter of its life, the main sequence. Our sun is in this phase, shining steadily for about 4.6 billion years, and with roughly 5 billion to go. Throughout the galaxy, countless stars of various sizes share this fate, turning hydrogen into helium in their cores, pouring light and heat into space. They are like the adults of the stellar family, some smaller, cooler, and redder, burning fuel slowly and destined to live extraordinarily long, tens to hundreds of billions of years. Others much larger, hotter, and bluer, burning furiously and living fast. Just a few million years, cosmic mayflies among stars. As time flows, even stars must change. When a star exhausts the hydrogen in its core, the delicate balance tips. Fusion slows. The core begins to contract under gravity and heats up, while the outer layers, freed from the core's pressure, expand outward. For a star like the Sun, this heralds transformation into a red giant. In a deep time vision, one would see the Sun swell many times its current size, perhaps engulfing Mercury, Venus, and even Earth. Its surface cools as it expands, shifting to a luminous orange-red hue, while its core grows hotter and denser until helium can fuse into carbon. For a while, the sun will juggle new reactions, shining not with its familiar white-yellow, but with the ruby light of old age. It may pulsate gently, shedding its outer layers in concentric waves of gas and dust. In its final breaths, it will cast off those layers entirely, creating a glowing planetary nebula, an expanding shell of gas lit by the hot, exposed core at the center. That core, no longer supported by fusion, will settle into a white dwarf, a hot, dense ember, roughly the size of Earth, but with most of the sun's mass, slowly cooling over billions of years. The nebula will disperse into the interstellar medium, seeding space with elements the sun forged, carbon, nitrogen, and more, gifts to the galaxy for future stars and planets. The white dwarf will fade from white to yellow to orange to red to black over trillions of years, a cinder in the darkness. Unless perhaps someday it flares again by accreting matter from a neighbor, as in a nova or supernova, if it had a companion. Such is the quiet finale for a medium star like the Sun. For stars much more massive than the Sun, the end is far more spectacular and violent. These titans, over about 8 solar masses, burn their fuel at a frantic rate, living only a few million years. They blaze hot and blue-white, and after fusing hydrogen to helium in their core, they proceed to fuse helium into carbon and oxygen, then heavier elements in layered shells, neon, magnesium, silicon, all the way to iron. Iron is a dead end. Fusing iron consumes energy instead of releasing it. So a massive star builds up an iron core like ash from a fire. Once the core is largely iron and grows to about 1.4 solar masses, it can no longer support itself against gravity. Thermal pressure and electron degeneracy pressure fail. In literally seconds, the core collapses. Protons and electrons mash together into neutrons, releasing a flood of neutrinos. The core implodes until neutron degeneracy and repulsive nuclear forces halt the collapse abruptly, and then it rebounds. This rebound, aided by neutrino pressure, launches a shockwave outward. The star's outer layers are blown off in one of nature's most cataclysmic events. A supernova explosion, briefly outshining all the billions of other stars in its galaxy. The debris, now rich in those heavy elements beyond iron, which are forged in the incredible temperatures of the explosion, is hurled into interstellar space. This supernova remnant will eventually mix with other gas and perhaps condense into new stars and planets. Meanwhile, the collapsed core remains. If the star's initial mass was moderately high, say 8 to 20 solar masses, the core becomes a neutron star, an object of mind-boggling density, about the size of a city, but with more mass than the Sun, composed mostly of neutrons. It spins rapidly. A newborn neutron star might rotate dozens of times per second, and has a powerful magnetic field, often becoming a pulsar that beams radiation like a lighthouse. If the star was extremely massive, the core collapse overwhelms even neutron degeneracy. No known force can withstand the gravity, and it continues collapsing into a black hole, a region of space-time from which nothing can escape. In either case, something remarkable happens. A once brilliant star ends in a tiny, dark remnant. If a neutron star or black hole is in a binary system, it might later accrete matter and produce X-ray emissions or further explosions, novae, X-ray bursts, etc. This cycle of stellar birth, life, and death is the heartbeat of cosmic evolution. Stars are not eternal. They are born, they mature, they grow old, and they die, often in a way that seeds the next generation. When the first generation of massive stars in the early universe died as supernovae, they produced and scattered the first heavy elements. Those enriched the gas from which new stars formed, including ones smaller, like the Sun, that could host planets with complex chemistry. Indeed, our solar system formed about 4.6 billion years ago from a cloud seeded by earlier stars' deaths, evidenced by radioactive isotopes in meteorites that are products of supernova explosions. Thus, we live in a universe where death begets new life. Supernovae create the raw material for planets and life. Even the gentle expulsion of a red giant's envelope, forming a planetary nebula, returns material to space that can be recycled. Carl Sagan's famous line, "We are made of star stuff," speaks literally true. The carbon in our proteins, the calcium in our bones, the iron in our blood, were all forged in stellar furnaces and spread by stellar deaths. Deep time connects to our very being.
The evolution of galaxies. Stars live within galaxies, and galaxies themselves change over cosmic time. Galaxies can be thought of as ecosystems of stars, gas, dust, dark matter, and star clusters, all interacting. Over billions of years, galaxies grow and transform, often through mergers with other galaxies. The early universe likely had many smaller protogalaxies that gradually coalesced into the large galaxies we see today. The Milky Way, for example, has consumed several smaller galaxies in its history, and continues to do so. We see streams of stars in our halo that are remnants of devoured dwarf galaxies. Spiral galaxies like ours likely formed when smaller gas-rich pieces merged, and the combined rotation settled into a disk. Galaxies evolve from one form to another. Two spiral galaxies merging may form an elliptical galaxy, losing their delicate spiral structure in a gravitationally violent embrace and triggering massive bursts of star formation as gas clouds collide and coalesce. Over time, ellipticals, which have little cold gas left after such bursts, become dominated by older, redder stars and have less ongoing star formation. Spirals, if left relatively unperturbed, can keep forming stars as they draw gas inward or accrete from their surroundings, but they too can run low on fuel. Our Milky Way is fated in about 4 to 5 billion years to merge with the Andromeda Galaxy, which is currently about 2.5 million light-years away and closing in at 110 km. Despite the enormous number of stars in each galaxy, hundreds of billions, individual stellar collisions are very unlikely due to vast interstellar spaces. However, the gravitational interaction will distort both galaxies dramatically. Over a few billion years, the two will likely settle into a single larger elliptical galaxy, sometimes dubbed Milkomeda. Simulations show their beautiful spiral arms will be thrown into chaotic streams. A burst of star formation may occur as gas clouds slam together. Ultimately, a more spheroidal distribution of stars will result. For any creatures alive then, perhaps far descendants of humanity or other intelligences, the night sky will transform. At first, Andromeda grows larger, then the sky fills with a blaze of new star formation and tidal tails of stars, and eventually it settles to a hazy glow of an elliptical galaxy filling the sky. The sun, by then a red giant or white dwarf, will find itself in a vastly altered cosmic neighborhood. Galaxies also evolve internally. Young galaxies, in the early universe, were often clumpy and irregular, forming stars at high rates. The peak of star formation in the cosmos was around 3 to 4 billion years after the Big Bang. Since then, star formation has generally declined as the big galaxies used up much of their readily available gas. Today, many large galaxies, especially ellipticals, are red and dead, forming few new stars, populated mainly by the aging population born in earlier epochs. Spirals like the Milky Way still form stars, but at a moderate pace. The Milky Way turns about 1 solar mass of gas into new stars per year. Small dwarf galaxies, especially if isolated, may still be forming stars slowly or have spurts of activity when tidal interactions occur. Galaxies can also lose gas. In clusters, where dozens to thousands of galaxies reside, a small galaxy, speeding through the hot intracluster medium, can have its gas stripped, like a breeze blowing leaves off a moving car, a process called ram pressure stripping. This leaves it without fuel for new stars, turning a blue spiral into a reddish gas-poor one. Or a galaxy might have its gas consumed by rapid starbursts, or sucked into a central black hole's accretion disk, active galactic nucleus, again quenching star formation. We observe many cluster galaxies that have this quenched appearance. Speaking of black holes, nearly every large galaxy has a supermassive black hole at its center, with masses from millions to billions of suns. In youth, when gas was abundant, these black holes likely powered quasars and active nuclei, sometimes expelling jets and winds that influenced their host galaxies. The interplay between central black holes and galaxy evolution is an area of active research. These black holes might help regulate star formation by heating or expelling gas, a kind of feedback. Thus, galaxies change both from external events, collisions, interactions, and internal dynamics, using up or losing gas, the effects of supernova and black hole feedback. Over deep time, the population of galaxies shifts. Fewer spirals exist now than in the past. Some have merged into ellipticals, and more ellipticals and lenticulars, disk galaxies without much gas or spiral structure, populate clusters. In the far future, as mentioned, accelerating expansion will isolate groups of galaxies. It's thought that in about 100 billion years, if dark energy remains constant, distant galaxies beyond our local group will have moved out of view, leaving future observers in our locale with only the merged Milky galaxy and its satellites visible, effectively a cosmic island, with little evidence of the wider universe's existence. They would see an apparent static cosmos of one galaxy, unaware of the greater cosmic web that we now behold. Black holes and the long future. Among the remnants of deep time, black holes stand as perhaps the most enigmatic. A star leaves behind a neutron star or black hole. Galaxies have supermassive black holes at their cores. Over extremely long times, black holes may become the dominant living things as stars burn out. A typical stellar black hole, tens of solar masses, will persist far, far longer than the current age of the universe. But even black holes aren't forever. Stephen Hawking showed that they slowly evaporate by emitting Hawking radiation due to quantum effects near the event horizon. A black hole, the mass of the Sun, would take 67 years to evaporate, an almost inconceivable span. Supermassive black holes take even longer, 100 plus years. But on the scale of deep time beyond star-filled eras, after all normal matter decays or is ejected, eventually black holes too will leak away their mass and disappear in a final burst of radiation. So imagine the stages of deep time. Now, the stelliferous era, full of stars shining. In about 100 trillion years, the last stars, likely low-mass red dwarfs and white dwarfs cooling into black dwarfs, will fade, the end of the era of starlight. What follows is sometimes called the degenerate era, the universe populated by degenerate remnants, white dwarfs, neutron stars, black holes, and cold brown dwarfs and planets. Collisions among these remnants could occasionally spark new activity. Two brown dwarfs merging might form a brief red star, or two white dwarfs colliding might ignite a supernova. But overall, it's a slow, dim time. Over quadrillions of years, gravitational encounters will gradually unbind most remaining stellar remnants from galaxies. Stars get flung out into the intergalactic void, one by one. Planets will fall into white dwarfs or be ejected. Eventually, even our Milky Way remnant, whatever it becomes after merging with Andromeda, will lose most of its constituents, and the galaxy as a gravitationally bound system will dissolve. Then comes the black hole era. After 1040 or 1050 years, depending on mass distributions, virtually everything left gravitating in lumps are black holes, from massive ones to possibly an army of micro-black holes, if any were created, though unlikely naturally. They slowly evaporate. The universe is dark, except perhaps for occasional flashes when black holes finish evaporating, or rare collisions between remnants. After an absurdly long time, all black holes evaporate too. We reach the final stage, some call the dark era.
only subatomic particles remain, mostly photons, neutrinos, electrons, and positrons, spread so thin across an ever-expanding cosmos that on average years of travel would be required to hit another particle. The temperature everywhere will be effectively absolute zero, apart from quantum fluctuations. The cosmos will have reached maximum entropy, no available free energy to do anything, essentially a quiet heat death. This long view, from bright Big Bang to faint heat death, is mind-bending. It makes our era of galaxies and stars and life seem like a fleeting springtime in the cosmos. And indeed, it is. Yet knowing this timeline can inspire an even greater appreciation for the now. We live in a special time when the universe is full of light and complexity. The deep future, though bleak in prospect, is fortunately trillions of times farther away than the current universe's age, so for all practical purposes, the cosmos will remain lively far, far longer than it has existed so far. Deep time narratives invite us to face both the resilience and impermanence of the cosmos. Stars die, but their remains fertilize new stars. Galaxies collide destructively, but forge new stars in the process. Even black holes might eventually die, but perhaps releasing whatever information they held. Through an emotional lens, these are stories of cosmic reincarnation and renewal, followed eventually by an end of things. An arc with a beginning and end, just as mythologies had, but on incomprehensible scales. To an immortal being watching eons pass, the universe would appear as a vast garden. Stars bloom like cosmic flowers, some short-lived and brilliant, others steady and enduring, then wither, their substance becoming the seeds of new blooms. Galaxies grow by gathering these blooms, sometimes pruning each other in collisions, and eventually many go to seed themselves as diffuse clouds. The garden analogy falters by the end of time, when darkness covers all. But by then, the garden had given all it could. For us, understanding deep time is at once enlightening and sobering. It contextualizes our brief lives in something far larger. It reminds us that change is constant. No arrangement of matter lasts forever. Yet it also shows how creative the universe has been in the time allotted, going from near uniform gas to conscious beings pondering it all. Now, with a grasp of deep time's canvas, we can zoom back to our human scale and ask, how do we, conscious flickers in this vast unfolding, fit in? The next chapter turns to the emergence of something arguably as remarkable as any galaxy, consciousness, which allows the cosmos to reflect on itself. Scale. As we zoom from the cosmic to the minute, we encounter a remarkable truth. Patterns repeat and echoes sound across vastly different scales. The universe is structured hierarchically, from subatomic particles up through atoms, molecules, planets, stars, galaxies, and the cosmic web. And while each layer has its unique phenomena, sometimes the small and large reflect each other in surprising ways. Imagine scaling down from human size. Shrink 1 billion times. You stand at the edge of an atom, electrons whizzing in a cloud around a tiny nucleus. The nucleus, if you peeked in, is itself a swarm of protons and neutrons, bound tightly by the strong force. Dive further. Inside a proton, you'll find quarks darting amid a sea of gluons. This is a world measured in femtometers, 10 to 15 me, and less, a far cry from everyday scales. Now zoom out, past human scale to planetary and beyond. The Earth orbits the Sun at 150 million km. The Sun orbits the center of the Milky Way, 27,000 light-years away, along with hundreds of billions of other stars. Our galaxy, 100,000 light-years across, is one of perhaps 100 billion in the observable universe. The largest coherent structures we see, walls of galaxies and voids, span a few billion light-years. That's a factor of about 10,040 from the Planck length, mine 10
to 35 MUDs, believed to be a fundamental scale of quantum gravity, to the observable universe's diameter, 10 to the 27 MU. Yet through this immense range, the same fundamental principles operate. Gravity holds planets in orbit much as it holds galaxies in clusters, just with different relative influences of other forces. Electromagnetism binds an electron to an atomic nucleus and similarly governs the structure of a star via plasma interactions. The forces of nature are scale-blind. They work everywhere, with only their effects modulated by environment. The small and the large often mirror each other. Consider a hydrogen atom, a tiny nucleus with electrons in orbit, historically likened to a miniature solar system. That analogy isn't perfectly accurate. Quantum mechanics shows electrons are in fuzzy probability clouds, not neat orbits. But the structural motif of a central mass with orbiting bodies recurs. Electrons around nuclei, moons around planets, planets around stars, stars around galaxy centers. The binding forces differ, electromagnetic versus gravitational. But the resulting patterns have a visual resonance. A spiral galaxy with its arms may evoke the swirl of water down a drain, or the spiral of a hurricane. Not because they are caused by the same reasons, gravity versus pressure and Coriolis forces, but because rotating systems often settle into spirals to conserve angular momentum and form density waves. One fascinating comparison: the cosmic web of galaxies and the network of neurons in a brain have been noted to share similar filamentary structures. One is billions of light years across, the other confined to a skull, but both are vast networks shaped by growth rules. A 2020 study even quantified similarities in the distribution of matter in the cosmic web and neural networks. While obviously the physics differ, the abstract analysis of connectivity showed parallels in complexity. It's a reminder that complexity can emerge from simple rules at multiple scales, sometimes yielding convergent structures. Our sense of scale is very limited to the human range. We measure in meters and seconds suited to our everyday life. But the universe extends far above and below those. A cosmic perspective forces us to accommodate scales where our intuition fails. It's mind-bending that an atomic nucleus, with its protons and neutrons, is as small relative to us as the sun is large relative to us. We sit roughly in the middle of logarithmic scales, about 10 2 meters in size. On a log plot from the Planck length to the universe, humans are not far from center. In a way, we have 1 foot in the micro-world. We can examine things as small as molecules and atoms with effort. And 1 foot in the cosmic. We can see galaxies and clusters with our telescopes. Perhaps this accident of scale is what allowed us as a species to comprehend things far beyond our direct sensory realm. We evolved in a world where both small and large phenomena affected us, from grains of sand to the cycling sun and moon, giving us curiosity in both directions. And indeed, modern science is a triumph of exploring both the very small and very large. By going down to subatomic scales, we've uncovered the fundamental particles and forces enabling technologies like electronics and nuclear energy. By going up to cosmic scales, we've discovered the Big Bang, cosmic expansion, and the age of the universe. The fact that the human mind, a small-scale object itself, can grasp scales 10-20 times smaller and 10-20 times larger than itself is astonishing. It's a testament to mathematics and imagination that we can conceptualize things so far outside direct experience. Another connection across scales is that the very large was seeded by the very small. Quantum fluctuations, random tiny variations at the subatomic level, during the epoch of inflation in the extremely early universe, were blown up to macroscopic size, laying down the pattern for the cosmic web. Thus, the distribution of clusters and voids we see today is in part a fossil record of quantum events in the first 10 to 30 seconds of the universe. The microscopic shaped the telescopic. This is almost poetic. The initial graininess on the quantum level
became the literal grains, galaxies, in the cosmic structure. Conversely, understanding large-scale processes often helps reveal small-scale physics. For example, observing the nuclear reactions in the Sun via neutrinos and helioseismology confirmed our knowledge of particle physics, like the properties of neutrinos. The solar neutrino problem and its resolution in neutrino oscillations showed neutrinos have mass, a small-scale property discovered by looking at a star. Cosmology data, like the microwave background and element abundances, provide evidence for particle physics phenomena, like the existence of relativistic species, neutrinos, in the early universe. In summary, the cosmos is truly fractal-like in its wonders. Patterns and principles iterate, and insight at one scale often informs another. We find ourselves at an intermediate scale, but equipped with tools and reason to traverse the extremes. By doing so, we realize that we are not isolated at our scale. We are made of subatomic particles, and we orbit a star in a galaxy. We contain multitudes of atoms, and we are part of something larger, the universe. Embracing this multi-scale reality adds to our awe. The next time you hold a salt crystal, consider that within its tiny cubic structure lies a microcosm of electromagnetic forces and quantum rules, not entirely unlike the gravitational lattice of galactic clusters spanning millions of light years. The salt's sodium and chlorine atoms form a repeating pattern, just as galaxies form a weave in space. Patterns at vastly different scales can still rhyme. Now, stepping back from scale and structure, we venture into what might be the strangest aspects of the cosmos. Those that challenge our understanding not just of size or shape, but of reality itself. Black holes that warp space-time, mysterious dark matter and dark energy that we detect only indirectly, hypothetical wormholes that might tunnel through space-time, and other unknowns that remind us how much more there is to learn. It's time to explore the strange cosmos, the mysterious components and possibilities that push the boundaries of known physics. The strange cosmos. For all that we have learned, the cosmos still guards many secrets. In fact, the more we've discovered, the more we've realized how much lies in darkness, hidden from direct perception. The night sky we see, with its stars and galaxies, is only a thin slice of reality. The rest is filled with mysteries, unseen matter and energy, space-time oddities, cosmic phenomena that challenge our intuition. Among these enigmas are black holes, dark matter, dark energy, and the hypothetical wormholes and parallel universes that tantalize physicists and philosophers alike. These are the strange elements of the cosmos that make it not just vast, but deeply mysterious. Black holes, the abyss of space-time. Perhaps nothing in the universe is as foreboding and fascinating as a black hole. Imagine a star 10 times the sun's mass reaching the end of its life. Its core fuel spent, it collapses under its own weight. If nothing stops the collapse, and for a massive core nothing will, it shrinks past the formation of a neutron star, past any known stable form, to a point, a singularity, of seemingly infinite density. All that mass is now concentrated in zero volume, and gravity around it becomes so intense that within a certain radius, the event horizon, not even light can escape. A black hole is born, an object with a one-way surface. Cross the event horizon, and you cannot return or send a message out. To the outside world, you effectively vanish. Black holes take our understanding of physics to the edge. According to Einstein's general relativity, mass curves spacetime. A black hole is an extreme curvature where spacetime essentially pinches off. Time and space swap roles in a sense. Moving forward in time inevitably carries you inward toward the singularity if you're inside the horizon. Quantum physics adds further mystery. At the event horizon, quantum effects can create particle pairs, leading to Hawking radiation, meaning black holes aren't completely black. They glow faintly and lose mass over time. We have strong evidence black holes exist. Stellar black holes announce themselves by gravitational effects on companions and by emitting X-rays when consuming gas. We have imaged the shadow of a 6 billion solar mass black hole in galaxy M87 via the Event Horizon Telescope, seeing a ring of light from hot gas and a dark center where the hole's gravity prevents light from coming directly to us. We see stars at the center of our Milky Way whipping around an invisible 4 million solar mass object at speeds of thousands of km/h. Definitely a supermassive black hole. So black holes are not just theoretical. They are out there. Commonplace, in fact. Every large galaxy likely has one, and many stellar remnants become black holes. They distort reality around them. Clocks near a black hole run slower relative to far away. To a distant observer, a clock falling toward a black hole appears to tick ever slower and essentially freeze at the horizon, though the clock itself experiences falling through normally. If you fell in, past tidal forces ripping you apart, if it's a small hole, you might have some time to observe near the singularity, but ultimately you'd be crushed, and what's inside the horizon is cut off from our universe, so it's like you've left our reality. Black holes are strange because they present a breakdown of our laws. A singularity is a sign that general relativity gives infinite results, meaning the theory breaks down there. It's expected that quantum gravity, a future theory uniting GR and quantum mechanics, will resolve what happens at the core. Do singularities exist, or are they replaced by something like a quantum fuzz or bounce? Also, do black holes destroy information? Quantum theory says information, the specifics of matter that fell in, should be preserved in some form. This has led to the famous black hole information paradox. Many physicists now think information does escape in subtle form via Hawking radiation or is stored in correlations, meaning black holes might not erase information entirely, no cosmic delete button, just very scrambled output. Even more exotic is speculation that a black hole could connect to another region of space-time, a wormhole. In principle, the mathematics of GR allow an Einstein-Rosen bridge connecting two black holes, or a black hole and a hypothetical white hole, essentially a tunnel. But such wormholes, if they exist, would be unstable. They'd pinch off unless held open by negative energy, exotic matter. We have no evidence wormholes exist naturally. They might be purely theoretical or require technology far beyond us to stabilize. Still, they captivate the imagination as cosmic shortcuts or even time machines, since wormholes potentially could allow travel back in time, raising paradoxes. Dark matter, the hidden mass. In the 1970s, astronomer Vera Rubin measured how fast stars orbit in the outer parts of spiral galaxies and found something odd. They were moving as fast as stars closer in. According to Newtonian gravity, stars far from the galactic center should orbit more slowly if most mass is concentrated in the center, like planets in the solar system. Instead, galaxy rotation curves flatten out, indicating there's much more gravity, and hence mass, in the outskirts than can be accounted for by visible stars and gas. Similarly, clusters of galaxies have galaxies moving too quickly to be held together by the visible mass alone, and gravitational lensing, the way clusters bend background light, indicates more mass than seen. The conclusion: most of the matter is unseen, dubbed dark matter. Dark matter seems to interact gravitationally, but not, or extremely weakly, via electromagnetic or nuclear forces. It doesn't emit, absorb, or scatter light, hence dark. It's not made of atoms. It's something else, likely some kind of particle left over from the Big Bang that we have yet to detect in the lab. It outweighs normal matter roughly 5.1 in the universe. It's the scaffolding on which galaxies formed, as discussed in the cosmic web. Without dark matter, our models struggle to form galaxies as observed, and structures might not hold together. Despite decades of trying, we haven't directly observed dark matter particles on Earth. Various underground detectors have looked for them hitting nuclei, without confirmed success yet, or created them in colliders. We infer their existence from their gravitational effects. The leading hypothesis is that dark matter is some kind of WIMP, weakly interacting massive particle, left from the early universe, or possibly an axion, a very light particle, or something more exotic like a dark sector with its own forces. But so far, it's a shadowy presence, clearly there, yet elusive. Some have proposed alternative gravity theories, like MOND, modified Newtonian dynamics, or various relativistic extensions, to eliminate the need for dark matter by changing how gravity works at galaxy scales. While these can fit some galaxy rotation curves, they struggle with cluster lensing and the cosmic microwave background data that strongly support the dark matter paradigm. The simplest consistent explanation remains a dominant component of unseen matter. So, to an extent, we live in a shadow universe. Only about 1/6 of matter is the familiar atoms that make up stars, planets, and us. The rest, plus an even larger fraction in dark energy, which we'll get to, is hidden. It's humbling. All the glowing galaxies are like a froth on a vast dark ocean of matter. Without that ocean, though, the froth wouldn't exist. Dark matter's gravity was essential to gather normal matter into galaxies. Dark energy, the runaway expansion. In 1998, two teams measuring distances to far supernovae made a shocking discovery. Distant type Ia supernovae were dimmer than expected, indicating they were farther than they should be if the universe's expansion was slowing down. Put simply, the expansion of the universe has been speeding up in the last few billion years. This was the opposite of what most expected. Gravity from matter should slow expansion. The cause was dubbed dark energy, a mysterious form of energy that fills space and drives accelerated expansion. It's often associated with the cosmological constant, L, concept that Einstein once introduced and famously discarded as a blunder when he thought the universe was static, now revived as a physical reality. Dark energy is even more enigmatic than dark matter. It constitutes about 68% of the universe's total energy content. We don't know what it is. If it's a true cosmological constant, it's an inherent property of space. Every cubic meter of vacuum has some fixed tiny energy, around 6 by 10 hours to 10 joules, that doesn't dilute as space expands. So as space grows, more vacuum means more total energy, causing expansion to accelerate. Alternatively, dark energy might be a field that can change over time, sometimes called quintessence, or something even more exotic, like an effect of other dimensions or a flaw in GR on huge scales. So far, all observations, supernova, cosmic microwave background, large-scale structure, are consistent with dark energy being a constant property of space, with an equation of state parameter, WL1, in cosmological terms. If it remains so, the fate is an ever-accelerating expansion. Galaxies outside our local group will recede faster and faster until they become unreachable and eventually invisible. Dark energy seems to have become dominant a few billion years ago. Prior to that, matter's gravity was slowing expansion. But as the universe expanded, matter diluted, density dropping as volume increases, whereas dark energy, as a constant density, did not. Eventually, matter's influence waned and dark energy took over, causing expansion to accelerate. Why dark energy has the value it does is a huge puzzle. Quantum zero-point energy calculations naively predict a cosmological constant, 10^120 times larger, which would have blown the universe apart instantly after the Big Bang. A gross discrepancy, one of the biggest in physics. Something, perhaps a cancellation mechanism we don't understand, leaves a small residual that is our dark energy. That's a major unsolved problem. If dark energy is constant, the universe will approach a de Sitter state, exponential expansion forever. If it's not constant, who knows? Some theorize dark energy could decay or even reverse, leading to a big crunch or oscillation, but no evidence of such behavior yet.
So we live in a universe where about 95% of its content is in two invisible forms, dark matter and dark energy. It's as if we have a book where only some letters are visible and the rest are in invisible ink. We're trying to read the story from the few visible letters and a lot of blank spaces. Yet the visible letters, stars, galaxies, etc., give us enough clues through their dynamics and arrangements to infer what's missing. Wormholes and other wild ideas. The notion of wormholes, shortcuts through space-time, has long captured imagination. Solutions of Einstein's equations, like the Schwarzschild wormhole, which is the non-traversable mathematical connection in a black hole solution, or the traversable Morris-Thorne wormholes that require exotic matter with negative energy, indicate such tunnels are not forbidden by general relativity outright. But whether nature actually makes any is unknown. If cosmic strings, defects in spacetime from early universe phase transitions, or certain quantum fluctuations occurred, some think it might be possible a few wormholes were spawned, but they'd likely collapse quickly or be extremely tiny. No evidence exists for any. If one could stabilize a wormhole, it could allow faster than light travel, effectively by taking a shortcut, or even time travel, depending how the wormhole mouths move relative to each other. But physics as we know it strongly suggests causality violations are not allowed. Time travel leads to paradoxes, though closed time-like curves can exist in theory. Most physicists suspect some deeper principle prevents actual time machines. Another wild idea: maybe our whole universe is a patch inside a larger multiverse, where other universes have different physical constants or particles. Inflation theory suggests space might be much larger than our observable part, possibly with other bubble universes disconnected from ours. If so, maybe constants like gravity's strength or protons' mass could vary in those bubbles. That could partially explain why our constants are tuned for life, anthropic selection from many universes. But this remains speculative and arguably untestable. We can't observe other universes if they're truly disjoint. Some signatures like colliding bubble universes might imprint something in our cosmic background, but none clearly seen. It might be that what we call constants of nature are not fixed in space-time either. There are studies testing if, say, the fine structure constant, electromagnetic strength, or electron-proton mass ratio has changed over cosmic time by analyzing ancient light. So far, results are mostly consistent with no change, or changes so slight they remain debated. If any drift exists, it's very tiny, meaning the laws today were essentially the laws 10 billion years ago. All these strange aspects, wormholes, multiverses, varying constants, stretch the boundaries of the known. They are at the edge of science and veer into philosophy at times because they're hard to verify or falsify. Still, exploring them is valuable. It expands our conception of what might be possible and forces us to confront the assumptions in our accepted theories. Embracing mystery. Confronting the strange cosmos instills humility. We see that our knowledge, while vast compared to the ancients, may still be scratching the surface. We uncovered dark matter and energy by their gravitational footprints, but we don't yet know their identities. We theorized black holes from relativity, then found they are real astrophysical objects, yet at their core lies the need for a new theory, quantum gravity, to understand singularities. We use quantum mechanics and relativity daily in our devices and GPS, yet their reconciliation into one framework eludes us, hinting at deeper layers of reality. The strange elements of the cosmos are clues that the story isn't finished. There are chapters of physics yet to be written, perhaps by future generations. And yet, rather than these unknowns making the universe seem alien, they can also inspire a sense of being part of a grand quest. We alive today are among the first generation to know that dark matter and dark energy exist. Perhaps one day a child today will solve the riddle of dark matter in a lab experiment or theory. We stand on a threshold where the cosmos is telling us there's more here than meets the eye. In grappling with the strange, we also find a reassuring continuity. Every time our view expanded or was challenged by Copernicus, by Hubble, by dark energy's discovery, we eventually integrated it and found our understanding actually deepened and often benefited humanity. Imagine modern tech without quantum mechanics or relativity, which were once strange new ideas. So there is faith, born of experience, that confronting the unknown is worthwhile, and reality, however strange, is ultimately comprehensible, as Einstein mused. Now, having explored the structure and mysteries of the external cosmos, we turn inward to perhaps the most remarkable outcome of cosmic evolution, ourselves, conscious beings capable of reflecting on the cosmos. We examine how the universe, through life and mind, has awakened to itself, and what that means for meaning and perspective. Consciousness. At some point in cosmic history, the cosmos became aware of itself, on at least one planet and perhaps countless others, a collection of atoms organized in such a way that it could ponder the very stars that made its constituents. This phenomenon, consciousness, is the most complex and mysterious form of order we know. Through us, and beings like us, the universe has eyes to see and minds to contemplate its own vastness. Carl Sagan put it poetically, "We are a way for the universe to know itself." The journey to consciousness was gradual and took billions of years on Earth. Simple life emerged at least 3.5 billion years ago in Earth's oceans, likely as self-replicating molecules that became enclosed in membranes, primitive cells. These life forms could sense and respond. Even a bacterium will move toward nutrients or away from harm. That's a rudimentary form of awareness, not thought, but biological feedback. Multicellular life allowed differentiation, specialized cells for sensing, like light-sensitive patches that became eyes, and for processing, simple neural nets. By the Cambrian explosion, 540 million years ago, complex animals with eyes and nervous systems filled the seas, presumably experiencing basic perceptions. Fast forward, vertebrates developed more complex brains. Some lineages crawled onto land. In mammals, the brain's cortex expanded, enabling memory, learning, and emotion. At some indeterminate point, early humans or their ancestors achieved self-awareness, an ability not just to feel or learn, but to know that they know, to reflect on one's own existence. Consciousness is hard to define but intimately known to each of us. It's the subjective experience of internal and external reality. It's the I am behind your eyes, the experiencer of your life. Scientifically, we map its correlates, brain patterns, neural oscillations, integrated information, but we don't truly understand how the grey matter of the brain produces the bright light of consciousness. This is the hard problem of consciousness. Yet, it undeniably does, at least in humans, and likely other animals to varying degrees. From a cosmic perspective, consciousness is profound because it seems qualitatively different from unconscious matter. The ingredients that make a human, oxygen, carbon, hydrogen, nitrogen, calcium, etc., are common in the cosmos, in air and rock and sea, but arrange them in the exquisite complexity of a living cell, then an organ, then a brain, and something novel emerges, mind. It raises a question. Is consciousness a fundamental aspect of the universe? Some philosophers and physicists have toyed with panpsychism, that consciousness might be a property of matter under certain conditions. Or is it an emergent phenomenon requiring a certain level of complexity? Either way, the potential for mind was built into the cosmos from the start, in the sense that the laws of physics allowed matter to self-organize into conscious forms.
When the universe was a hot plasma, it had no structures at all, let alone life. But it cooled, matter clumped, stars forged heavier elements, planets formed with complex chemistry, life sparked and evolved, and eventually, those ancient atomic nuclei, born in the hearts of stars, became part of a thinking being that can look back and say, "Wow, I come from the stars." The cosmos became aware of its origins through our minds. This confers a sense of purpose, in a way. Not an externally assigned purpose, but a role we naturally play. We are the cosmos, in one of its latest evolutionary phases, marveling at itself. When we discover things about the universe, it is literally the universe discovering itself. Our joy of comprehension is the universe taking joy in self-comprehension. Consciousness also heightens the emotional stakes of cosmic knowledge. Without conscious beings, the grand universe simply is, with no one to admire a nebula or fear a black hole. With consciousness, beauty and terror enter the scene. Think of the first humans fearful of eclipses or awestruck by the Milky Way. The cosmos evokes feelings now because we feel. Through us, the universe has emotion and meaning, at least locally. A nebula is not objectively beautiful, but we find it so, giving aesthetic dimension to existence that wouldn't exist without minds. Many scientists and philosophers suspect life and possibly consciousness might not be unique to Earth. If biology is a natural outcome on wet, rocky worlds under the right conditions, and evolution often fosters intelligence given enough time, then perhaps the cosmos teems with other conscious beings. They may not be human-like, but they could wonder and seek as we do. Perhaps the universe has many centers of consciousness scattered among the galaxies, a kind of cosmic self-awareness shining in many places. Or perhaps not. Maybe intelligent life is extremely rare. We don't know yet. Either answer, teeming life or cosmic solitude, is profound. If we are among many, what a grand community awaits discovery, though distances are forbidding. If we are alone, or nearly so, what a precious flame of awareness we bear, and what responsibility to not squander it. Consciousness gives the universe a way to know time in a meaningful way too. Without minds, time just passes. With minds, the passage of time is felt. We have memory of the past and anticipation of the future. We seek patterns and thus uncover cosmic history, like figuring out the Big Bang, and cosmic future, heat death or other fates. In a sense, by becoming aware of deep time, we have extended the reach of consciousness to the entire lifespan of the universe. Mentally, we travel to the beginning and to hypothetical ends. The universe through us can contemplate its entire existence, almost like how we as individuals reflect on our own lives. There is also a contemplative aspect. Many find that recognizing we are the universe coming to consciousness can be spiritually meaningful. It collapses the divide between me and world. In a cosmic sense, the distinction is indeed arbitrary. We're made of the world and return to it. As conscious beings, we can feel empathy not just to other living things, but to the stars and the atoms, feeling a unity with all. Some spiritual traditions echo this scientific truth. We are one with the universe. As we move forward, conscious of our conscious role, we might ask, what next for the cosmos and consciousness? Will our awareness fade when humanity, or life, ends, or will it spread? Some dream of humanity expanding to other planets, carrying consciousness further through the cosmos. In doing so, giving the universe more places where it can reflect on itself. Others consider that artificial intelligence might carry consciousness, or at least intelligence forward, even if biological life fails. It's a speculative territory, but the point remains. Through our minds, the universe has reached a level of self-reflection, and what we do with that is, to some extent, up to us. Having considered mind and meaning, let's pull back one last time to the broadest perspective. Is our universe the only one? Or could there be a multitude, a multiverse? And is the structure of reality fundamentally made of something like information or math, rather than tangible matter? These are deep questions at the intersection of physics and philosophy. We touch on them briefly, as they color the ultimate context in which our cosmos might reside. The multiverse. Is our universe unique, or one of many? For ages, universe meant all there is. But modern physics has opened the door to the idea that our universe might be a bubble in a froth of countless universes. A multiverse. This concept arises from several lines of thought. One is cosmic inflation, the idea that a fraction of a second after the Big Bang, space expanded exponentially fast. Inflation theory, in many versions, suggests that inflation didn't end everywhere at once. It ended in patches, like our universe, while other regions kept inflating, budding off other bubble universes. If eternal inflation is correct, our universe may be one domain among an indefinitely large, possibly infinite number of domains, each a universe in its own right, with potentially different properties. Another motivator is fine-tuning. We observe that certain fundamental constants, like the strength of electromagnetism or the dark energy density, have values in a narrow range that allows complexity, galaxies, stars, life, to exist. It's puzzling why they have just those life-permitting values. One possible explanation is the anthropic principle combined with a multiverse. If indeed many universes exist with varying constants, we naturally find ourselves in one of the minority that by chance has the right conditions for observers, because only such universes get observers. It's like we shouldn't be surprised to live on Earth rather than on Jupiter. Only Earth had the proper conditions for our kind of life. Similarly, maybe only a small fraction of universes have viable physics for any form of complexity, and of course, we must be in one of those. If the multiverse idea is true, reality is much bigger than we can see. Our observable cosmos, the 93 billion light-year bubble of space we can currently observe, would be just a tiny patch in an inconceivably vast inflating space that contains other bubbles beyond our horizon. We cannot directly communicate with or travel to those other universes. Space between us and them is still inflating, or they're causally disconnected. But their existence would answer some otherwise intractable why questions by essentially saying everything happens somewhere. We see what we see because those conditions are necessary for us to exist. In some multiverse scenarios, the basic laws might differ. Perhaps one universe has a slightly stronger, strong force, which might mean no hydrogen, all protons fuse into heavier elements quickly, or a slightly weaker electromagnetic force. Maybe stars can't form because fusion won't ignite. There might even be universes with different numbers of spatial dimensions or different particle types. The possibilities are vast in principle. We don't know if physical constants can vary like that. But string theory, for instance, predicts a landscape of possible vacuum states with different properties, and eternal inflation could populate different regions with different vacuum states, hence different constants and particle physics. It's almost a philosophical question. Are these other universes real if we can never observe them? Some say if a theory that predicts them also robustly predicts things we can observe, and the theory is validated, then we must accept whatever else it entails, like unseen universes. Others argue that non-disprovable entities are not within science's remit. Currently, the multiverse is a hypothesis, intriguing, sometimes seemingly implied by theories but not confirmed.
Parallel to the cosmological multiverse is the idea from quantum mechanics of the many worlds interpretation, that every quantum event that has multiple outcomes, electron goes left or right, spawns branches of reality for each outcome. In that view, all possible histories consistent with quantum probabilities play out in a vast branching of universes. This is a different beast than the inflationary multiverse. These universes occupy the same space but in different quantum branches, rather than separate bubbles of space. But interestingly, Both ideas paint a picture of numerous alternate realities. If both were true, it could be an unimaginably enormous collection of universes, bubble universes, each with internal branching quantum worlds. These ideas challenge our notion of uniqueness. It might make one feel small. Not only are we one tiny planet in a vast universe, but our entire universe might be one grain of sand on an endless cosmic shore. But one can also find it empowering. If indeed our universe is rare enough to permit life, how lucky we are to experience it. If universes are countless, then the creative potential of reality is truly without limit. Whatever can happen will happen somewhere, perhaps many times over. One might ask, how does multiverse thinking affect daily life or meaning? Perhaps not much. True or not, it doesn't change the tangible universe we interact with. But it adds another layer to the grand perspective, maybe even our entire cosmic cosmos, a journey through space and time.